Imagine, if you will, that you could step away from Earth, float in the infinite expanse of space, and observe our blue planet suspended in the darkness. From this cosmic perspective, Earth appears as a perfect sphere, serene, almost unchanging. But as we drift closer, we begin to discover that nothing is truly still. Clouds move like white brushstrokes across the oceans. Continents reveal their mountains, their winding rivers, their forests that change with the seasons. And if we continue approaching, if we could descend to the cities, the streets, the homes, down to the people who walk, work, and sleep, we would discover something extraordinary. Each human being you see is not truly one organism, but rather a walking ecosystem, a universe unto themselves, teeming with life that is both foreign and essential. We are not alone in our own bodies. We never have been. Tonight, as you settle into rest, we invite you on a gentle journey into the invisible world that lives within us all. A world so vast, so complex, and so intimately connected to who we are, that scientists are only now beginning to understand its profound influence on our health, our emotions, our very identity. This is the story of the microbiome, our second self, the trillions of microscopic partners that have shaped human evolution and continue to shape our daily lives in ways we are only beginning to comprehend. You are not just you. You are a universe. You are an ecosystem. You are home to countless forms of life that work in harmony to keep you alive, healthy, and uniquely yourself. This is their story. This is your story. Let us begin our descent into the microscopic realm that exists beneath your skin, inside your breath, throughout your body. Let us explore the invisible world inside us. Origins of our microbial partners. The story of your microbiome begins before you take your first breath. It begins in the warm, sterile sanctuary of your mother's womb, where for 9 months you develop in a world essentially free of microbes. You float in amniotic fluid, receiving nutrients through the umbilical cord, growing in a space that is uniquely yours and yours alone. But this solitary existence is brief. The moment you are born, everything changes. Your first breath brings with it not just oxygen, but an entire universe of microscopic life. The journey from sterile womb to microbial-rich world is perhaps the most dramatic transition you will ever experience, though you will have no memory of it. If you were born through natural childbirth, your first passengers were likely lactobacilli and bifidobacteria from your mother's birth canal. These pioneer species began colonizing your skin, your mouth, your nascent gut, establishing the first communities of your lifelong microbial companions. Each species finding its preferred habitat, each beginning the work of transforming your sterile body into a thriving ecosystem. If you entered the world through cesarean section, your first microbial encounters were different. Instead of your mother's vaginal microbes, you were likely colonized first by skin bacteria from the hospital environment, from the hands that delivered you, from the air itself. This difference in initial colonization has fascinated researchers for decades, as studies suggest it may influence immune development and health outcomes throughout life. Your first meal also shaped your microbial destiny. If you were breastfed, you received not just nutrients, but specific oligosaccharides complex, sugars that your own enzymes cannot digest. These molecules serve as food specifically for beneficial bacteria like bifidobacteria, helping them flourish in your developing gut. Breast milk is, in essence, not just food for you, but food for your microbes, a carefully orchestrated system evolved over millions of years to establish the healthiest possible microbial community. The environment you entered also left its mark on your microbial identity. The pets in your home, the dust on the floors, the people who held you each contributed to the diverse library of microbes that would become part of you. Children raised in homes with pets often develop more diverse microbiomes. Those who grow up on farms, surrounded by animals and soil bacteria, tend to have robust microbial communities that may protect against allergies and autoimmune conditions later in life. This early colonization period, roughly the first 3 years of life, is critical. During this time, your microbiome develops its basic structure, establishes its major communities, and begins the complex process of training your immune system. The bacteria teaching your body what is friend and what is foe, what deserves an immune response and what should be tolerated. The discovery of these microbial partners is a relatively recent chapter in human understanding. For most of human history, bacteria were viewed primarily as agents of disease. The pioneering work of Louis Pasteur and Robert Koch in the 19th century established the germ theory of disease, revolutionizing medicine, but also creating a somewhat adversarial relationship between humans and microbes. It wasn't until 1885 that German pediatrician Theodor Escherich first described the bacteria living in the human gut, discovering what we now call E. coli. His observations marked the beginning of our understanding that not all bacteria are harmful, that some might actually be beneficial residents of the human body. Through the 20th century, researchers slowly began to piece together the complexity of our microbial relationships. They discovered that certain bacteria could synthesize vitamins, aid in digestion, and even protect against harmful pathogens. But it wasn't until the advent of DNA sequencing technology, in recent decades, that we truly began to understand the vast scope of our microbial universe. Dr. Jeffrey Gordon, a pioneering microbiologist at Washington University, describes the moment researchers first began to grasp the true diversity of gut bacteria. We realized we weren't just looking at a few dozen species, but hundreds, even thousands of different microorganisms, each with their own genetic capabilities, their own metabolic functions. We were looking at a forgotten organ. Pediatrician Dr. Maria Santos reflects on how understanding of early microbial colonization has changed medical practice. We now understand that those first few days and months of life are crucial for establishing a healthy microbiome. The decisions we make about delivery method, feeding, antibiotic use, they all have consequences that can last a lifetime. This early microbial inheritance is part genetic lottery, part environmental circumstance, and part the choices made by your parents and caregivers. But it is only the beginning of your microbial story. Throughout your life, your microbiome will continue to evolve, responding to your diet, your environment, your medications, your stress levels, your sleep patterns, even your social interactions. The microbes you carry today are different from those you carried as a child, and they will be different again tomorrow. You are in constant dialogue with the microbial world, constantly gaining new species, losing others, maintaining a dynamic balance that is as unique as your fingerprint. As we drift deeper into understanding this invisible ecosystem, we begin to realize that the question is not whether we can live without our microbes, but whether we would still be ourselves without them. They are not merely passengers in our biological journey, they are active participants, co-pilots in the complex process of being human. The gut as a command center. Deep within your abdomen lies an organ that weighs about the same as your brain and contains more nerve cells than your spinal cord. This organ processes the food you eat, manufactures essential vitamins, communicates constantly with your brain, influences your mood, and plays a crucial role in determining your weight. Yet, until recently, most people thought of it merely as the place where food goes to be digested. Your gut microbiome is far more than a collection of digestive aids. It is a sophisticated biological computer, processing information, making decisions, and sending signals throughout your body 24 hours a day. The 3 pounds of bacteria Viruses, fungi, and other microorganisms that live in your intestines represent the most metabolically active part of your microbiome, and perhaps the most influential. When you eat, you are not just feeding yourself. You are feeding trillions of microscopic partners, each with their own dietary preferences, each contributing to the complex process of extracting energy and nutrients from food. But this process is far more nuanced than simply breaking down what you eat. Your gut bacteria actively influence how many calories your body extracts from food, which nutrients are absorbed, and how those nutrients are metabolized. Consider the remarkable case of Sarah, a 32-year-old teacher who struggled with weight management for years. Despite following identical diets and exercise routines as her friends, Sarah found it much easier to gain weight and much harder to lose it. For years, she blamed her metabolism, her genetics, her willpower. It wasn't until she participated in a microbiome study that researchers discovered the likely culprit. Her gut bacteria were extraordinarily efficient at extracting calories from food. Sarah's microbiome was dominated by bacteria called firmicutes, which are particularly good at breaking down dietary fiber and converting it into short-chain fatty acids that the body can use for energy. Her friends, who seemed to eat with impunity, had microbiomes dominated by bacteroidetes, which are less efficient at calorie extraction. Sarah wasn't lacking willpower. She was hosting a community of microbes that were almost too good at their job. This discovery led Sarah to work with nutritionists who understood the microbiome. By adjusting her diet to favor the growth of bacteroidetes and limit the proliferation of firmicutes, she was able to gradually rebalance her gut ecosystem. The changes weren't immediate. It took months for her microbiome to shift significantly, but over time, her body began responding differently to food. The same meals that once led to weight gain now supported a healthier weight. Research led by Dr. Ruth Lay at Cornell University has revealed that the ratio of firmicutes to bacteroidetes in the gut can vary dramatically between individuals and may be one factor influencing obesity risk. In studies of identical twins where one twin is obese and the other is lean, the obese twin consistently shows a different microbial profile, often with a higher ratio of firmicutes to bacteroidetes. But the influence of gut bacteria on weight goes beyond simple calorie extraction. These microbes produce hundreds of metabolites, chemical compounds that can influence appetite, metabolism, and fat storage. Some bacteria produce compounds that increase insulin sensitivity, helping the body process glucose more effectively. Others produce metabolites that influence the production of hormones like leptin and ghrelin, which regulate hunger and satiety. Dr. Patrice Canny, a researcher at the University of Louvain in Belgium, has spent years studying how gut bacteria influence metabolism. His research has shown that certain beneficial bacteria can strengthen the gut barrier, reducing inflammation and improving metabolic health. We've discovered that the gut microbiome acts like a metabolic thermostat, Dr. Canny explains. It helps determine how efficiently we burn calories, how we store fat, and how our body responds to different foods. The implications of this research extend far beyond individual weight management. Twin studies have provided some of the most compelling evidence of the microbiome's role in metabolism. In groundbreaking experiments, researchers have transplanted gut bacteria from obese and lean twins into germ-free mice. The mice that received bacteria from obese twins gained more weight, while those that received bacteria from lean twins remained lean, even when fed identical diets. These experiments suggest that obesity may be, at least in part, a microbial condition. The bacteria in your gut today were influenced by your early life experiences, your diet over the years, medications you've taken, stress you've experienced, and countless other factors. But unlike your genes, your microbiome can be changed. Take the case of Michael, a 45-year-old accountant who had struggled with diabetes for over a decade. Despite medication and dietary changes, his blood sugar remained difficult to control. When he enrolled in a clinical trial studying fecal microbiota transplantation for metabolic disorders, researchers discovered that his gut microbiome lacked several key species known to help regulate glucose metabolism. The treatment involved transplanting gut bacteria from a healthy donor with excellent metabolic health. Within weeks, Michael's gut microbiome began to resemble that of the donor. His blood sugar levels started stabilizing. His insulin sensitivity improved. 6 months later, he was able to reduce his diabetes medication significantly. The idea that we might treat metabolic disorders by modifying gut bacteria is still experimental, but it represents a fundamental shift in how we think about conditions like obesity and diabetes. Rather than seeing these as purely genetic or behavioral conditions, we're beginning to understand them as ecosystem disorders, problems that arise when the microbial community in our gut becomes imbalanced. Dr. Imran Mayer, a gastroenterologist at UCLA who has studied the gut-brain connection for decades, describes the gut microbiome as the body's second brain. The gut contains over 500 million nerve cells, more than in the spinal cord, and these nerves are in constant communication with the bacteria that live there. When you feel hungry, your gut bacteria may be sending signals to your brain. When you crave certain foods, your microbes may be influencing those desires based on their own nutritional needs. The bacteria that thrive on sugar may increase sugar cravings. Those that prefer fiber may influence you to seek out vegetables and whole grains. This microbial influence on appetite and food preferences helps explain why dietary changes can be so difficult to maintain. When you suddenly change your diet, you're not just fighting your own habits and cravings, you're also working against the established microbial community in your gut, which may resist changes that threaten their survival. But this same system can work in your favor. As you consistently eat foods that support beneficial bacteria, those species proliferate and may begin to influence your cravings in healthier directions. People who maintain plant-rich diets often report that over time, they begin to crave vegetables and lose their taste for highly processed foods. This isn't just psychological adaptation. It may reflect changes in their gut microbiome. The metabolism-regulating power of gut bacteria extends to the production of essential nutrients. Certain bacteria synthesize vitamins, including several B vitamins and vitamin K. Others produce short-chain fatty acids that serve as fuel for the cells lining your colon and have anti-inflammatory effects throughout the body. Some bacteria help metabolize bile acids, influencing cholesterol levels and cardiovascular health. Your gut bacteria even influence how you respond to medications. Some bacteria can metabolize drugs before they're absorbed, reducing their effectiveness. Others can convert inactive compounds into active medications, potentially increasing their potency. This microbial metabolism of medications is an emerging field of study that may eventually lead to personalized medicine based on individual microbiome profiles. The circadian rhythm of your gut bacteria also plays a role in metabolism. Just as your body has internal clocks that regulate sleep and wake cycles, your gut bacteria have their own daily rhythms. These bacterial cycles influence when you feel hungry, how efficiently you process food, and how your body stores energy. Disruptions to these rhythms from shift work, jet lag, or irregular eating patterns can disturb both your microbial ecosystem and your metabolic health. Recent research has even suggested that the timing of meals may be as important as their content for maintaining a healthy microbiome and optimal metabolism. Intermittent fasting, for example, appears to influence the composition and activity of gut bacteria in ways that may support metabolic health. As you rest tonight, your gut bacteria continue their work, processing the food from your last meal, synthesizing nutrients, communicating with your immune system, and preparing your body for tomorrow. They are partners in your metabolism, collaborators in your health, silent workers in the complex process of turning food into energy, nutrients into building blocks, meals into the fuel that keeps you alive. The command center in your gut never sleeps, never stops, never ceases its intricate dance with your body's systems. It is a testament to the profound interconnectedness of life, the way that organisms can work together in harmony to create something greater than the sum of their parts. The chemical conversations. Within your body, a constant stream of chemical messages flows between you and your microbial partners. These conversations, conducted in the language of molecules and metabolites, are so fundamental to your existence that you cannot truly understand human biology without understanding microbial communication. Every second, your gut bacteria produce thousands of different chemical compounds. Some of these molecules are metabolites, the products of bacterial digestion and metabolism. Others are signaling compounds designed specifically for communication. Together, they form a complex chemical vocabulary that influences everything from your immune responses to your emotional state. Consider serotonin, often called the happiness neurotransmitter. Most people associate serotonin with the brain, where it plays crucial roles in mood regulation, sleep, and appetite control. But here's a remarkable fact. About 90% of your body's serotonin is produced not in your brain, but in your gut, and its production is significantly influenced by your gut bacteria. Certain species of bacteria, particularly those in the genus Enterococcus and Streptococcus, can directly produce serotonin. Other bacteria influence serotonin production by gut cells themselves. The tryptophan in your diet found in foods like turkey, eggs, and cheese serves as raw material for serotonin synthesis. But gut bacteria help regulate this process, determining how much tryptophan is converted to serotonin versus other compounds. This microbial influence on serotonin production helps explain the profound connection between gut health and mental well-being. When your gut microbiome is disrupted by antibiotics, illness, stress, or poor diet, serotonin production can be affected, potentially influencing mood, sleep patterns, and emotional resilience. The case of Jennifer, a 28-year-old graphic designer, illustrates this connection beautifully. After a severe bout of food poisoning that required treatment with powerful antibiotics, Jennifer found herself struggling with anxiety and depression for months. Her doctor initially attributed these symptoms to the stress of her illness, but when her mental health symptoms persisted long after her physical recovery, further investigation revealed significant disruption to her gut microbiome. Working with a gastroenterologist who understood the gut-brain connection, Jennifer began a carefully planned program to restore her microbial diversity. She introduced fermented foods, took targeted probiotics, and adjusted her diet to support the growth of serotonin-producing bacteria. Gradually, as her gut microbiome recovered its diversity and balance, her mood symptoms improved. The anxiety that had plagued her began to lift, her sleep quality improved, and she felt more like her pre-illness self. Jennifer's experience reflects a growing body of research showing that the gut-brain axis, the bidirectional communication pathway between gut bacteria and the central nervous system, plays a crucial role in mental health. This communication occurs through multiple channels: the vagus nerve, which directly connects the gut to the brain, the immune system, which responds to bacterial signals, and the bloodstream, which carries bacterial metabolites throughout the body. Dr. John Cryan, a neuroscientist at University College Cork in Ireland, has been at the forefront of research into what he calls psychobiotics, beneficial bacteria that can influence mental health. His studies have shown that certain probiotic strains can reduce anxiety and depression symptoms in both animal models and human trials. We're beginning to understand that the microbiome is like a second brain, Dr. Cryan explains. It's constantly sending signals that influence mood, cognition, and behavior. Depression and anxiety may not just be brain disorders, they may be ecosystem disorders. The chemical conversations between your bacteria and your brain involve dozens of different neurotransmitters and neuromodulators. Gut bacteria can produce GABA, the brain's primary inhibitory neurotransmitter, which promotes calm and reduces anxiety. They produce dopamine, which influences motivation and reward-seeking behavior. They create acetylcholine, which plays roles in attention and learning. But the microbial influence on brain function goes beyond neurotransmitter production. Gut bacteria also produce metabolites that can cross the blood-brain barrier and directly influence neural activity. Short-chain fatty acids, produced when bacteria ferment dietary fiber, have anti-inflammatory effects in the brain and may protect against neurodegenerative diseases. The inflammatory potential of gut bacteria represents another crucial aspect of their chemical communication with your body. When your gut microbiome is balanced and diverse, the bacteria generally produce anti-inflammatory compounds that help maintain immune homeostasis. But when the ecosystem becomes disrupted, a condition called dysbiosis, harmful bacteria can proliferate and produce inflammatory compounds that may contribute to a wide range of health problems. Lipopolysaccharides, or LPS, are molecules found in the outer membrane of certain bacteria. When these bacteria die and release LPS, or when the gut barrier becomes compromised and allows LPS to enter the bloodstream, they can trigger inflammatory responses throughout the body. This leaky gut phenomenon has been implicated in conditions ranging from inflammatory bowel disease to cardiovascular disease to depression. Dr. Alessio Fasano, a pediatric gastroenterologist at Massachusetts General Hospital, has spent decades studying gut barrier function and its relationship to health and disease. His research has shown that the integrity of the gut barrier, the lining that separates gut bacteria from the rest of the body, is crucial for maintaining health. The gut barrier is like the security system of the body, Dr. Fasano explains. When it's functioning properly, it allows beneficial nutrients to pass through, while keeping potentially harmful bacteria and their toxins contained. But when this barrier becomes compromised, we see inflammation and immune dysfunction that can affect virtually every organ system. The maintenance of gut barrier integrity is itself a collaborative effort between you and your bacteria. Beneficial bacteria produce compounds that strengthen the tight junctions between gut cells, reinforcing the barrier. They also produce mucus-stimulating factors that help maintain the protective mucus layer lining the gut. In return, a healthy gut barrier provides an optimal environment for beneficial bacteria to thrive. This symbiotic relationship can be disrupted by various factors: chronic stress, which can weaken the gut barrier and alter bacterial composition; antibiotics, which can reduce bacterial diversity and allow harmful species to overgrow; processed foods high in additives and low in fiber, which can feed harmful bacteria while starving beneficial ones; and chronic inflammation from any source, which can create a cycle of gut barrier dysfunction and bacterial imbalance. The chemical conversations between your microbes extend beyond the gut-brain axis to include complex interactions with your immune system. Your gut bacteria are in constant dialogue with immune cells, training them to distinguish between friend and foe, helping them respond appropriately to threats while avoiding unnecessary inflammation. This immune education begins in early life and continues throughout your lifetime. Beneficial bacteria present antigens to immune cells in a controlled manner, helping to calibrate immune responses. They produce metabolites that can suppress excessive immune activation while enhancing the body's ability to fight genuine threats. Children who grow up with reduced microbial diversity, perhaps due to overuse of antibiotics, overly sterile environments, or limited exposure to different microbes, may develop immune systems that haven't been properly educated. This can lead to increased risk of allergies, asthma, and autoimmune conditions later in life. The hygiene hypothesis, first proposed by epidemiologist David Strachan, suggests that some exposure to microbes during early life is necessary for proper immune development. While cleanliness is certainly important for preventing infectious diseases, an overly sterile environment may deprive the developing immune system of the microbial teachers it needs to function optimally. Your gut bacteria also influence your body's production of antimicrobial peptides, natural antibiotics, that help fight harmful bacteria while preserving beneficial ones. They regulate the production of immunoglobulin A, an antibody that helps protect mucosal surfaces throughout the body. They even influence the development and function of immune cells in distant organs, including the brain, lungs, and skin. The metabolic conversations between you and your bacteria are equally complex and consequential. Beyond their role in digestion and calorie extraction, gut bacteria influence hormone production, vitamin synthesis, and detoxification processes throughout the body. Certain bacteria can metabolize estrogen, influencing hormone levels in ways that may affect reproductive health, bone density, and cardiovascular function. Others can convert dietary compounds into bioactive metabolites that have anti-cancer properties. Some bacteria can even break down environmental toxins, serving as a first line of defense against harmful chemicals. The production of vitamins by gut bacteria represents one of the most direct examples of how these microbes contribute to human health. Bacteria in your gut synthesize several B vitamins, including folate, biotin, and vitamin B12. They produce vitamin K, which is essential for blood clotting and bone health. The amount of vitamins produced by your gut bacteria can vary significantly based on the composition of your microbiome and your dietary choices. This microbial vitamin production helps explain why vitamin deficiencies can sometimes develop even in people with seemingly adequate diets. If gut bacteria capable of producing certain vitamins are depleted, perhaps by antibiotic treatment or dietary changes, vitamin status can be affected regardless of dietary intake. The chemical conversations occurring within your body right now, as you listen to these words, represent millions of years of evolutionary partnership between humans and microbes. These molecular dialogues are so sophisticated, so finely tuned, that they make human language seem simple by comparison. Every meal you eat changes the chemical vocabulary of these conversations. Every medication you take influences the messages being sent. Every stressful event, every good night's sleep, every laugh with friends subtly alters the complex chemical symphony playing out in your gut. As you prepare for sleep tonight, know that these conversations will continue. Your bacteria will process the nutrients from your evening meal, produce compounds that influence your sleep quality, maintain your immune defenses, and prepare your body for tomorrow's challenges. They are speaking a language older than words, conducting conversations more intimate than any you will have with another human being. You are never truly alone, never truly silent. You are the host to trillions of chemical conversationalists, partners in the complex business of being human, collaborators in the magnificent dance of life. The immune system's microbial teachers. In the quiet moments before sleep, as your body settles into rest, your immune system continues its vigilant watch. But this surveillance system, which protects you from countless threats every day, was not born knowing friend from foe. It learned through patient instruction from trillions of microbial teachers that have been shaping human immunity for millennia. Your immune system's relationship with your microbiome is perhaps the most sophisticated example of biological cooperation on Earth. From the moment you were born, bacteria began the delicate process of educating your immune cells, teaching them when to fight, when to tolerate, and when to heal. This education begins in infancy with remarkable precision. Beneficial bacteria present their molecular signatures to developing immune cells in controlled amounts, like showing flashcards to a student. These early lessons help establish immune memory, the ability to recognize and respond appropriately to different microorganisms throughout life. Children born by cesarean section and those treated with antibiotics in early life sometimes miss crucial lessons in this microbial curriculum. Without proper immune education from diverse gut bacteria, they may develop immune systems that overreact to harmless substances, leading to allergies and asthma, or underreact to genuine threats, increasing infection risk. The story of immune education through microbial exposure unfolds differently across cultures and environments. Children raised on traditional farms, surrounded by diverse animals and soil bacteria, often develop remarkably resilient immune systems. The Amish communities of Pennsylvania, whose children grow up with extensive animal contact and limited antibiotic use, show dramatically lower rates of allergies and autoimmune diseases compared to their urban counterparts. Dr. Mark Halbry, an allergist who has studied Amish communities for years, describes their children's immune profiles as old-school robust, well-calibrated, and resistant to the inflammatory overreactions that characterize modern allergic diseases. These children's immune systems learned from a diverse faculty of microbial teachers, he explains. Their bacteria taught them wisdom that urban children often miss. This microbial education occurs primarily in your gut, where specialized immune cells called dendritic cells constantly sample bacterial products. Like border guards checking passports, these cells examine molecular signatures from gut bacteria and decide whether to mount an immune response or maintain peaceful coexistence. Beneficial bacteria have evolved sophisticated ways to communicate their peaceful intentions to immune cells. They produce metabolites that suppress excessive inflammation while maintaining protective responses against genuine pathogens. They strengthen the gut barrier that separates bacterial communities from immune cells, preventing unnecessary alarms. They even influence the development of regulatory T cells, immune cells specialized in maintaining tolerance and preventing autoimmune reactions. The case of Maria Elena illustrates the profound impact of this immune microbiome relationship. As a child growing up in rural Mexico, she was exposed to a diverse array of environmental bacteria from animals, soil, and traditional fermented foods. Her immune system learned to coexist with this microbial diversity, developing robust tolerance mechanisms that served her well throughout childhood. When Maria Elena moved to a major U.S. city for college, her microbial exposure changed dramatically. Urban environments, processed foods, and occasional antibiotic treatments gradually altered her gut microbiome. Over several years, she began developing food sensitivities and seasonal allergies that she had never experienced before. Her immune system, having lost some of its microbial teachers, began reacting to previously tolerated substances. Working with an integrative medicine physician who understood the immune-microbiome connection, Maria Elena began deliberately reintroducing microbial diversity into her life. She sought out traditionally fermented foods, spent more time in natural environments, and used targeted probiotics to restore beneficial bacteria that had been depleted. Gradually, her immune system regained some of its early wisdom, and her allergic reactions diminished. The immune system's dependence on microbial education extends beyond tolerance training to include active protection against pathogens. Beneficial bacteria don't just teach immune cells what not to attack, they also enhance the ability to fight genuine threats. Gut bacteria stimulate the production of antimicrobial peptides, natural antibiotics that can eliminate harmful bacteria while preserving beneficial ones. They enhance the function of neutrophils and macrophages, immune cells that serve as the body's first responders to infection. They even influence the production of antibodies that circulate throughout the body, providing protection at distant sites. Dr. Yasmine Belkade, an immunologist at the National Institute of Health, has spent years studying how commensal bacteria, the beneficial microbes that live peacefully in our bodies, shape immune function. Her research has revealed that these bacteria don't just coexist with our immune system, they actively participate in immune responses. We used to think of bacteria as either good or bad, Dr. Belkade explains. Now we understand that the relationship is much more nuanced. Our commensal bacteria are active partners in immunity, helping to calibrate responses, maintain tissue health, and protect against pathogens. This partnership is particularly evident in the production of immunoglobulin A, or IgA, the most abundant antibody in the human body. Ig coats mucosal surfaces throughout the body in the gut, lungs, mouth, and other areas where microbes are likely to be encountered. The production of Ig is heavily influenced by gut bacteria, which stimulate immune cells to produce this protective antibody. People with depleted gut microbiomes often have reduced Ig production, making them more susceptible to infections and inflammatory diseases. Conversely, those with diverse, healthy microbiomes typically have robust IgA responses that help maintain immune homeostasis. The microbial influence on immunity extends to tissues far from the gut through a phenomenon called the common mucosal immune system. Immune cells educated in the gut-associated lymphoid tissue can migrate to other mucosal sites throughout the body, bringing their microbially informed wisdom to the lungs, urogenital tract, and other organs. This helps explain why gut health can influence susceptibility to respiratory infections, urinary tract infections, and other conditions that might seem unrelated to intestinal bacteria. The immune cells patrolling your lungs right now may have received their training in your gut, learning from bacteria how to respond appropriately to the microbes they encounter in respiratory tissues. The seasonal patterns of infectious disease also reflect this immune-microbiome relationship. During winter months, when people spend more time indoors with less diverse microbial exposures, gut microbiome diversity often decreases. This reduction in microbial diversity can weaken immune function, contributing to increased susceptibility to respiratory viruses during flu season. Recent research has even suggested that the effectiveness of vaccines may be influenced by gut microbiome composition. People with more diverse gut microbiomes often develop stronger antibody responses to vaccinations, while those with depleted microbiomes may have reduced vaccine efficacy. The inflammatory balance maintained by gut bacteria is crucial for immune health. Chronic low-grade inflammation, often called inflammaging when it occurs with aging, has been linked to numerous health problems including cardiovascular disease, diabetes, and neurodegenerative conditions. Beneficial gut bacteria produce anti-inflammatory compounds that help prevent this harmful inflammation, while preserving the ability to mount protective immune responses when needed. Short-chain fatty acids produced by bacterial fermentation of dietary fiber have particularly potent anti-inflammatory effects. These molecules can directly influence immune cell function, promoting the development of regulatory T cells that help maintain immune tolerance. They also strengthen the gut barrier, reducing the translocation of inflammatory bacterial products into systemic circulation. The loss of these beneficial bacteria and their anti-inflammatory products may contribute to the increased inflammation seen in many modern chronic diseases. The Western diet, low in fiber and high in processed foods, often fails to support the bacteria that produce these protective compounds. Your circadian rhythms also influence the immune-microbiome relationship. Both immune cells and gut bacteria follow daily cycles that affect their activity and interactions. Disrupted sleep patterns can alter these rhythms, potentially affecting both microbial composition and immune function. During sleep, your immune system performs important maintenance functions, consolidating immune memories and clearing cellular debris. Your gut bacteria also show circadian patterns of activity that may influence these nighttime immune processes. The restoration that occurs during quality sleep depends partly on the coordinated activities of your immune cells and microbial partners. Stress represents another important factor in immune-microbiome interactions. Chronic stress can alter gut bacteria composition while simultaneously suppressing immune function, creating a vulnerability to both infections and inflammatory diseases. The stress hormones cortisol and adrenaline can directly influence bacterial growth and metabolism, favoring some species over others. Conversely, beneficial gut bacteria can influence stress resilience through their effects on the immune system and the gut-brain axis. Some bacteria produce compounds that can reduce inflammation in the brain and support resilience to psychological stress. This bidirectional relationship between stress, immunity, and microbiome creates feedback loops that can either support health or contribute to disease. The aging process also transforms the immune-microbiome relationship. As we age, our gut microbiome typically becomes less diverse, and our immune system may become less responsive to microbial signals. This immunosenescence can contribute to increased susceptibility to infections and chronic inflammatory diseases in older adults. However, maintaining a diverse gut microbiome through appropriate diet, exercise, and lifestyle choices may help preserve immune function with aging. Centenarians, people who live to 100 and beyond, often maintain surprisingly diverse gut microbiomes, suggesting that microbial diversity may be one factor contributing to healthy longevity. The therapeutic potential of understanding immune microbiome interactions is enormous. Researchers are developing new treatments based on modulating this relationship, from precision probiotics designed to enhance vaccine responses to fecal microbiota transplantation for treating immune-related diseases. As you rest tonight, your immune system continues its quiet vigilance, guided by lessons learned from countless microbial teachers. These microscopic instructors have shaped your body's defenses through millions of evolutionary partnerships, creating an immune system that is uniquely yours yet connected to the ancient wisdom of the microbial world. The brain-gut highway. In the depths of your abdomen runs a superhighway of communication that connects your gut directly to your brain. This pathway, called the vagus nerve, carries more than 500,000 nerve fibers and represents one of the most important communication channels in your entire body. Along this highway, messages flow constantly between your gut bacteria and your brain, influencing everything from your emotions to your memories to your basic survival instincts. The discovery that gut bacteria could influence brain function revolutionized our understanding of mental health, behavior, and even consciousness itself. For decades, the brain was viewed as a protected organ, isolated from the rest of the body by the blood-brain barrier, and immune to the influence of lowly intestinal bacteria. Today, we know this view was profoundly incomplete. Your gut produces more neurotransmitters than your brain. It contains more nerve cells than your spinal cord. It processes emotional information, forms memories, and influences decisions in ways that neuroscientists are only beginning to understand. And none of this happens in isolation from the trillions of bacteria that call your intestines home. The story of David illustrates the profound nature of the gut-brain connection. A successful architect in his 40s, David had always been known for his calm demeanor and sharp focus. But following a severe gastrointestinal infection during a business trip to Southeast Asia, everything changed. The infection cleared within a week, but in the months that followed, David found himself struggling with anxiety, brain fog, and mood swings that seemed to come from nowhere. His physician initially attributed these symptoms to stress from his illness, but as months passed without improvement, David sought help from a gastroenterologist who specialized in the gut-brain axis. Comprehensive testing revealed that the infection had dramatically altered David's gut microbiome, depleting several key bacterial species known to produce neurotransmitters and anti-inflammatory compounds. Working with both a psychiatrist and a nutritionist, David began a carefully orchestrated program to restore his gut health. He introduced specific probiotic strains known to support mental health, modified his diet to feed beneficial bacteria, and practiced stress reduction techniques that could help rebalance his gut-brain communication. The recovery was gradual but profound. Over 6 months, as David's gut microbiome regained its diversity and balance, his mental clarity returned. The anxiety that had plagued him began to subside. His mood stabilized, and he felt like himself again. The experience taught him that mental health and gut health were not separate concerns but aspects of a single, integrated system. Dr. Imran Mayer, director of the UCLA Center for Neuroscience, Stress and the Gut, has spent decades mapping the communication pathways between gut bacteria and the brain. His research has shown that this communication is bidirectional and constant. The gut is not just responding to signals from the brain, Dr. Mayer explains. It's actively sending signals that influence mood, cognition, and behavior. We're looking at a true partnership between brain and gut. The vagus nerve serves as the primary highway for this communication, but it's not the only route. Gut bacteria influence the brain through the immune system, releasing molecules that can trigger or suppress inflammatory responses in neural tissue. They communicate through the bloodstream, producing metabolites that can cross the blood-brain barrier and directly affect brain function. They even influence the brain through the enteric nervous system, the network of nerves embedded in the gut wall that some scientists call the second brain. This second brain contains over 500 million neurons, more than in the spinal cord. It can function independently of the central nervous system, controlling digestion, monitoring the chemical environment of the gut, and responding to the presence of different bacteria. But it also communicates constantly with the brain in your head, sending signals that can influence emotion, decision-making, and even personality. The production of neurotransmitters by gut bacteria represents one of the most direct ways that microbes influence mental function. Different bacterial species produce different neurotransmitters, creating a complex chemical symphony that affects brain activity. Lactobacillus species produce GABA, the brain's primary calming neurotransmitter. Enterococcus and Streptococcus species produce serotonin, influencing mood and sleep. Bacillus species produce dopamine, affecting motivation and reward processing. The implications of this bacterial neurotransmitter production are staggering. It suggests that depression, anxiety, and other mental health conditions may not be purely neurological disorders, but may also involve microbial imbalances. This has led to the development of psychobiotics, probiotic preparations, specifically designed to support mental health. Clinical trials of psychobiotics have shown promising results. Studies have found that certain probiotic strains can reduce symptoms of depression and anxiety as effectively as some conventional treatments. Other research has shown that probiotics can improve cognitive function, reduce stress responses, and even enhance memory formation. The case of Alina, a graduate student struggling with severe anxiety, illustrates the potential of this approach. Traditional anti-anxiety medications had provided only limited relief and came with side effects that interfered with her studies. When she learned about the gut-brain connection, she decided to try a comprehensive approach that included specific psychobiotic strains along with dietary changes to support beneficial bacteria. Within 8 weeks, Alina noticed significant improvements in her anxiety levels. Her panic attacks became less frequent and less severe. Her sleep quality improved, and she found herself better able to cope with academic stress. Blood tests showed reduced levels of inflammatory markers, and stool analysis revealed increased diversity in her gut microbiome, with significant growth in bacteria known to produce calming neurotransmitters. The influence of gut bacteria on brain function extends beyond neurotransmitter production to include the regulation of inflammation in neural tissue. Chronic inflammation in the brain has been implicated in depression, anxiety, cognitive decline, and neurodegenerative diseases. Beneficial gut bacteria produce anti-inflammatory compounds that can reduce this neuroinflammation, potentially protecting against mental health problems and cognitive decline. Short-chain fatty acids, produced when gut bacteria ferment dietary fiber, are particularly important for brain health. These molecules can cross the blood-brain barrier and have been shown to reduce inflammation in neural tissue, support the growth of new brain cells, and protect against neurodegenerative processes. The gut-brain axis also influences stress responses through its effects on the hypothalamic-pituitary-adrenal axis, the body's primary stress response system. Gut bacteria can influence the production of stress hormones like cortisol, affecting how the body responds to psychological and physical stressors. People with diverse, healthy gut microbiomes often show more resilient stress responses, with faster recovery from stressful events and less tendency toward chronic stress-related health problems. Conversely, those with depleted or imbalanced gut microbiomes may be more vulnerable to stress and its negative health effects. Sleep represents another important aspect of gut-brain communication. The quality and timing of your sleep can influence gut bacteria composition, while gut bacteria can affect sleep quality through their production of neurotransmitters and other bioactive compounds. This creates a feedback loop where poor sleep can worsen gut health, which in turn can further disrupt sleep. Many people find that improving gut health leads to better sleep quality, while prioritizing good sleep hygiene supports a healthier gut microbiome. The circadian rhythms that regulate sleep-wake cycles also influence bacterial activity in the gut, creating daily patterns of microbial metabolism that affect brain function. Memory formation and cognitive function are also influenced by the gut-brain axis. Studies in laboratory animals have shown that gut bacteria can affect learning and memory through their influence on brain-derived neurotrophic factor, a protein that supports the growth and survival of brain cells. Mice raised without gut bacteria show impaired memory formation and altered brain development. In humans, emerging research suggests that gut health may influence cognitive aging and the risk of neurodegenerative diseases. People with Alzheimer's disease often show distinct patterns of gut bacteria composition, with reduced diversity and increased levels of inflammatory bacteria. While it's still unclear whether these changes contribute to the disease or result from it, the correlation suggests that gut health may be an important factor in maintaining cognitive function throughout life. The social aspects of the gut-brain connection are particularly fascinating. Research has shown that gut bacteria can influence social behavior, empathy, and even personality traits. Animals with different gut bacteria compositions show different levels of social interaction, aggression, and exploratory behavior. In humans, the gut microbiome appears to influence social cognition and emotional processing. People with more diverse gut microbiomes often score higher on measures of emotional regulation and social connectivity. This may be because gut bacteria influence the production of neurotransmitters involved in social bonding and emotional processing. The development of the gut-brain axis begins in early life and is influenced by factors like birth method, feeding patterns, and early antibiotic exposure. Children who experience significant disruptions to their gut microbiome during critical developmental periods may be at increased risk for behavioral and cognitive problems later in life. Autism spectrum disorders, attention deficit hyperactivity disorder, and other neurodevelopmental conditions have all been associated with alterations in gut bacteria composition. While these associations don't prove causation, they suggest that the gut-brain axis may play a role in neurodevelopment, and that interventions targeting gut health might have therapeutic potential. The therapeutic applications of gut-brain axis research are expanding rapidly. Researchers are developing targeted probiotics for specific mental health conditions, exploring the use of dietary interventions to support brain health, and investigating how existing psychiatric medications might work partly through their effects on gut bacteria. Fecal microbiota transplantation, originally developed for treating infectious diseases, is being studied as a potential treatment for depression, anxiety, and other mental health conditions. Early results are promising, with some patients showing significant improvements in mood and cognitive function following microbiota transplantation. The personalized medicine implications of gut-brain axis research are profound. As we learn more about how individual differences in gut bacteria composition affect brain function, we may be able to develop personalized treatments based on each person's unique microbiome profile. Imagine a future where mental health treatment includes comprehensive analysis of gut bacteria, where antidepressants are prescribed alongside specific probiotics, where cognitive enhancement involves optimizing gut health as much as brain training. This future may be closer than we think. As you settle into sleep tonight, the communication along your gut-brain highway continues. Bacterial metabolites produced during the digestion of your evening meal travel through your bloodstream to your brain. Neurotransmitters manufactured by gut bacteria influence the quality of your dreams. The vagus nerve carries messages between your intestinal ecosystem and your sleeping mind, maintaining the constant dialogue that shapes your mental and emotional life. You are not just a brain controlling a body, or a body housing a brain. You are an integrated ecosystem where mind and microbes collaborate in the ongoing creation of consciousness, emotion, and thought. This partnership, evolved over millions of years, continues its work as you rest, preparing you for tomorrow's challenges and opportunities. When the ecosystem falls apart. In the delicate balance of your internal ecosystem, harmony can shift to chaos with surprising speed. When the microbial communities that have evolved to support your health become disrupted, the consequences can cascade through every system in your body. This disruption, known as dysbiosis, represents one of the most significant health challenges of modern life. The story of antibiotic-associated dysbiosis begins with a medical miracle. Antibiotics have saved countless lives since their discovery, transforming once fatal infections into treatable conditions. But these powerful medications are indiscriminate in their targeting, eliminating beneficial bacteria along with harmful pathogens. Each course of antibiotics is like a forest fire sweeping through your internal ecosystem, clearing away established communities and leaving vacant niches for opportunistic species to colonize. Consider the experience of Robert, a 55-year-old teacher who developed pneumonia during a particularly stressful period at work. The infection required treatment with a powerful broad-spectrum antibiotic, which quickly cleared his lung infection and likely saved his life. But in the weeks following his recovery, Robert began experiencing a cascade of new health problems that seemed unrelated to his original illness. First came digestive issues, bloating, irregular bowel movements, and food sensitivities he had never experienced before. Then his energy levels plummeted, leaving him feeling exhausted even after a full night's sleep. Most troubling of all, he began experiencing anxiety and mood swings that were completely unlike his usual steady temperament. Robert's physician initially attributed these symptoms to stress and the aftermath of his illness, but when the problems persisted for months, further investigation revealed what had really happened. The antibiotic treatment had dramatically reduced the diversity of his gut microbiome, eliminating beneficial species that had supported his digestion, immune function, and mental health. The recovery process was long and complex. Working with a gastroenterologist who understood the microbiome, Robert began a careful program to restore his bacterial diversity. He introduced fermented foods, took targeted probiotics, and modified his diet to support the growth of beneficial bacteria. Slowly, over the course of a year, his gut ecosystem began to recover. His digestive symptoms improved, his energy returned, and his mood stabilized. But his microbiome never quite returned to its pre-antibiotic state, a reminder of how fragile these internal ecosystems can be. Dr. Martin Blaser, an infectious disease specialist at Rutgers University, has spent decades studying the unintended consequences of antibiotic use. His research has shown that each course of antibiotics creates lasting changes in the gut microbiome, with some bacterial species never returning after elimination. We're gradually depleting our microbial heritage, Dr. Blaser explains. Each generation has less microbial diversity than the previous one, and we're only beginning to understand what we're losing. Some of these bacteria, once extinct from the human microbiome, may be gone forever. The modern epidemic of antibiotic overuse has created what some researchers call a microbiome crisis. In developed countries, the average person receives multiple courses of antibiotics during childhood and continues to receive them throughout life for both necessary and unnecessary reasons. Each exposure further reduces microbial diversity, creating populations with impoverished gut ecosystems. This loss of microbial diversity has been linked to the rise of numerous modern diseases. Asthma, allergies, inflammatory bowel disease, type 1 diabetes, and obesity have all increased dramatically in developed countries over the past several decades, paralleling the widespread use of antibiotics and the associated loss of microbial diversity. The mechanisms underlying these associations are becoming clearer as research advances. Reduced microbial diversity can impair immune system development, leading to increased susceptibility to allergic and autoimmune diseases. It can alter metabolism, contributing to obesity and metabolic disorders. It can disrupt the gut-brain axis, potentially increasing risk for mental health problems. Hospital-acquired infections represent another catastrophic form of dysbiosis. In healthcare settings, where antibiotic use is intensive and resistant bacteria are common, patients can develop severe disruptions to their gut microbiomes that leave them vulnerable to dangerous infections. Clostridioides difficile infection, or C. diff, illustrates this vulnerability dramatically. This bacteria can cause life-threatening colitis, but it typically only causes problems when the normal gut microbiome has been disrupted by antibiotics. In a healthy gut ecosystem, beneficial bacteria prevent C. diff from establishing itself through a process called colonization resistance. But when antibiotics eliminate these protective bacteria, C. diff can proliferate unchecked. The case of Margaret, an 80-year-old woman who developed C. diff infection following antibiotic treatment for a urinary tract infection, demonstrates both the devastating effects of severe dysbiosis and the remarkable potential for restoration. Margaret's infection was so severe that conventional antibiotic treatments failed to control it, and she faced the possibility of life-threatening complications. As a last resort, Margaret's doctors recommended fecal microbiota transplantation, essentially transplanting gut bacteria from a healthy donor to restore her disrupted ecosystem. The procedure itself was simple, but the results were dramatic. Within days, the C. diff infection was controlled. Within weeks, Margaret's gut microbiome had largely restored itself, incorporating the donated bacteria into stable, protective communities. Margaret's case illustrates one of the most promising therapeutic applications of microbiome science. Fecal microbiota transplantation has shown remarkable success rates for treating recurrent C. diff infections, often achieving cure rates above 90% when conventional treatments have failed. But dysbiosis extends beyond antibiotic-induced disruptions to include the slower, more insidious changes associated with modern lifestyle factors. The Western diet, high in processed foods and low in fiber, creates an environment that favors harmful bacteria while starving beneficial ones. Chronic stress can alter gut bacteria composition through its effects on immune function and gut barrier integrity. Environmental toxins, from pesticides to industrial chemicals, can disrupt microbial communities in subtle but significant ways. Dr. Erika Sonnenberg, a microbiologist at Stanford University, has studied how dietary changes affect gut bacteria composition. Her research has shown that the transition from traditional, fiber-rich diets to processed, Western-style diets can dramatically reduce microbial diversity within just a few days. The gut microbiome is like a garden, Dr. Sonnenberg explains. If you stop watering and fertilizing it properly, if you introduce toxins and disrupt the soil, the garden will gradually degrade. The same thing happens with our gut bacteria when we don't provide the right nutritional environment. The loss of specific bacterial species can have cascading effects throughout the ecosystem. Some bacteria serve as keystone species, supporting the growth and activity of many other microorganisms. When these crucial species are lost, entire communities can collapse, leading to simplified, less resilient microbial ecosystems. This loss of resilience means that disrupted microbiomes are more vulnerable to further disturbances. A person with reduced microbial diversity may be more susceptible to infections, more likely to develop antibiotic-resistant bacteria, and less able to recover from future disruptions. The intergenerational transmission of dysbiosis represents one of the most concerning aspects of the microbiome crisis. Children born to mothers with depleted gut microbiomes may inherit reduced microbial diversity from birth. This creates a ratcheting effect where each generation starts with less microbial diversity than the previous one. Environmental factors in early life can further compound this problem. Formula feeding, early antibiotic exposure, cesarean delivery, and limited contact with diverse microbial environments can all reduce the diversity of a child's developing microbiome. These early life factors may have lasting consequences for immune development, metabolic health, and disease susceptibility throughout life. The concept of microbial extinction has emerged as researchers recognize that some bacterial species may be permanently lost from human populations. Unlike plant and animal extinctions, which are visible and dramatic, microbial extinctions happen silently, often going unnoticed until researchers attempt to find specific species and discover they no longer exist in human populations. Some traditional populations that have had limited exposure to antibiotics and Western dietary patterns serve as reservoirs of microbial diversity that has been lost in developed countries. These communities may harbor bacterial species that could be crucial for understanding and treating diseases that have become common in industrialized societies. The restoration of disrupted microbiomes is possible but challenging. Unlike acute infections that can be cured with a single treatment, dysbiosis often requires sustained efforts to gradually rebuild microbial communities. This process may involve dietary changes, probiotic supplementation, probiotic consumption to feed beneficial bacteria, and lifestyle modifications to support microbial health. The success of restoration efforts depends on many factors, including the severity of the initial disruption, the individual's overall health status, and their ability to maintain supportive lifestyle changes. Some aspects of microbiome diversity may be restored relatively quickly, while others may take months or years to rebuild. Personalized approaches to microbiome restoration are becoming increasingly sophisticated as researchers develop better tools for analyzing individual microbial communities. Rather than using one-size-fits-all probiotic preparations, future treatments may be tailored to each person's specific microbial deficits and health needs. The prevention of dysbiosis represents an equally important frontier. This includes more judicious use of antibiotics, reserving these powerful medications for situations where they are truly necessary. It involves dietary education to help people understand how food choices affect their microbial communities. It requires environmental policies to reduce exposure to chemicals and toxins that can disrupt microbial ecosystems. Healthcare systems are beginning to recognize the importance of protecting microbial diversity. Some hospitals now use probiotic protocols to help maintain gut health in patients receiving antibiotics. Others are implementing antibiotic stewardship programs to reduce unnecessary antibiotic use. The field of precision medicine is incorporating microbiome analysis into treatment decisions. Before prescribing antibiotics, doctors may soon be able to analyze a patient's gut bacteria composition to predict which antibiotics are most likely to be effective, while causing the least collateral damage to beneficial bacteria. As you rest tonight, your gut microbiome continues its work of maintaining the delicate balance that supports your health. The bacteria in your intestines are engaged in constant competition and cooperation, establishing territories, sharing resources, and responding to the chemical signals that flow through your internal environment. This ecosystem has evolved over millions of years to support human health, but it faces unprecedented challenges in the modern world. The choices you make about diet, medication use, stress management, and environmental exposure all influence the stability and diversity of your microbial communities. The resilience of your internal ecosystem depends not just on its current composition, but on its ability to adapt and recover from disturbances. Like any ecosystem, it benefits from diversity, stability, and the right environmental conditions to thrive. By understanding the factors that can disrupt this delicate balance and the strategies that can help restore and maintain it, you become an active participant in caring for the trillions of microorganisms that call your body home. They, in turn, continue their ancient work of supporting your health, your immunity, and your very existence. The future of microbial medicine. In the quiet laboratories of research institutions around the world, scientists are discovering possibilities that would have seemed like science fiction just decades ago. They are learning to read the genetic signatures of bacteria like books, to design custom microbes for specific therapeutic purposes, and to treat diseases by restoring balance to the invisible ecosystems within our bodies. We stand at the threshold of a medical revolution that may transform how we understand and treat human disease. The story of precision microbiome medicine begins with the recognition that each person's microbial ecosystem is as unique as their fingerprint. Just as personalized medicine has moved beyond one-size-fits-all treatments to consider individual genetic variations, microbiome medicine is developing approaches tailored to each person's specific microbial composition and needs. Dr. Rob Knight, a pioneer in microbiome research at UC San Diego, describes the potential of this field. We're moving toward a future where we'll be able to analyze your microbiome, identify specific imbalances or deficiencies, and prescribe targeted interventions to restore optimal microbial function. It's like precision agriculture for the human body. The development of next-generation probiotics represents one of the most promising frontiers in this field. Unlike the limited strains available in current probiotic supplements, researchers are identifying and cultivating hundreds of beneficial bacterial species that could serve specific therapeutic purposes. These include bacteria that can produce specific vitamins, break down particular toxins, or modulate immune responses in precisely targeted ways. The case of a young boy named James illustrates the potential of this approach. Born with a rare genetic condition that prevented his body from producing certain essential amino acids, James faced severe developmental delays and life-threatening health complications. Traditional treatments had limited effectiveness, but researchers identified specific bacterial strains that could produce the missing amino acids in the gut. Working with regulatory agencies to develop a compassionate use protocol, doctors introduced these specially selected bacteria into James's gut microbiome. Over months, as these bacteria established themselves and began producing the needed amino acids, James's health gradually improved. His development accelerated, his energy increased, and his overall health stabilized. The bacteria had essentially become living factories within his gut, producing the molecules his genetic condition prevented his body from making. This approach of using bacteria as biological factories has enormous potential applications. Researchers are developing bacterial strains that can produce anti-inflammatory compounds for treating autoimmune diseases, neurotransmitters for supporting mental health, and even anti-cancer agents for targeted tumor therapy. The field of synthetic biology is pushing these possibilities even further. Scientists are learning to engineer bacteria with novel capabilities, creating microorganisms that can perform functions not found in nature. These engineered bacteria could serve as living sensors, detecting disease markers and responding with appropriate therapeutic compounds. Imagine bacteria that could monitor blood sugar levels and produce insulin as needed for diabetes management, or microbes that could detect early signs of cancer and release targeted treatments directly to tumor sites. These possibilities, once purely speculative, are now being developed in research laboratories around the world. Fecal microbiota transplantation, which has already shown remarkable success in treating C. diff infections, is being expanded to address a wide range of conditions. Clinical trials are underway testing FMT for inflammatory bowel disease, obesity, autism spectrum disorders, depression, and even neurodegenerative diseases. The story of Lisa, a 38-year-old woman with severe ulcerative colitis, demonstrates the life-changing potential of this approach. After years of failed treatments with conventional medications, Lisa was facing the possibility of surgical removal of her colon. As a last resort, she enrolled in a clinical trial testing FMT for inflammatory bowel disease. The treatment involved carefully screening potential donors for optimal gut health and microbial diversity, then transplanting their gut bacteria into Lisa's digestive system. The process was repeated several times over several months to ensure successful colonization of beneficial bacteria. The results exceeded everyone's expectations. Lisa's inflammation markers dropped dramatically. Her symptoms improved significantly. Colonoscopy examinations showed healing of intestinal tissue that had been damaged for years. 2 years later, she remains in remission, her gut ecosystem having been fundamentally reset by the transplanted bacteria. The success of FMT has led to the development of more refined approaches. Instead of transplanting entire microbial communities, researchers are identifying specific combinations of bacteria that provide therapeutic benefits. These defined microbial consortiums could offer the benefits of FMT while reducing risks and improving standardization. Pharmaceutical companies are investing heavily in developing these next-generation microbial therapeutics. Rather than being classified as supplements, these products are being developed as prescription medications, subject to rigorous clinical testing and regulatory approval processes. The diagnostic applications of microbiome analysis are equally promising. Researchers have identified microbial signatures associated with numerous diseases, from colorectal cancer to Alzheimer's disease to depression. These microbial biomarkers could enable earlier disease detection, more accurate diagnosis, and better monitoring of treatment responses. Dr. Pierre Bork, a computational biologist at the European Molecular Biology Laboratory, has developed machine learning algorithms that can predict disease risk based on gut microbiome composition. We can now look at someone's gut bacteria and make predictions about their health status with remarkable accuracy, he explains. This opens up possibilities for preventive medicine that we've never had before. The integration of microbiome data with other health information promises to create comprehensive health profiles that capture the complex interactions between genetics, lifestyle, environment, and microbial ecology. Artificial intelligence systems are being developed that can analyze these multidimensional datasets to provide personalized health recommendations and treatment plans. Preventive microbiome medicine represents another exciting frontier. Rather than waiting for diseases to develop, we may soon be able to identify microbial risk factors and intervene to prevent illness before symptoms appear. This could involve dietary modifications, targeted probiotic treatments, or lifestyle changes designed to optimize microbial health. The concept of microbiome-guided nutrition is already beginning to influence dietary recommendations. Researchers have discovered that individual responses to foods vary significantly based on gut bacteria composition. Some people's microbiomes are better suited to processing certain carbohydrates, while others may benefit from higher protein or fat intake based on their bacterial profiles. Companies are developing personalized nutrition programs based on individual microbiome analysis. These programs provide specific dietary recommendations designed to support optimal microbial balance and overall health. While still in early stages, initial results suggest that microbiome-guided diets may be more effective than generic dietary recommendations. The agricultural and food production implications of microbiome research are equally significant. Scientists are developing probiotic foods specifically designed to support beneficial gut bacteria. They are creating fermented products with targeted bacterial strains for specific health benefits. Some researchers are even exploring how agricultural practices affect the microbial content of foods and how this might influence human health. Environmental microbiome management represents another emerging field. Researchers are studying how the built environment affects human microbial exposure and developing strategies to create spaces that support healthy microbial ecosystems. This could influence everything from hospital design to urban planning to architectural standards for homes and schools. The global health implications of microbiome medicine are profound. Many diseases that disproportionately affect developing countries may be linked to microbial factors influenced by sanitation, nutrition, and antibiotic access. Understanding these connections could lead to more effective interventions for global health challenges. Conversely, the loss of microbial diversity in developed countries suggests that some traditional practices and foods may have important health benefits that modern medicine is only beginning to understand. This has led to renewed interest in traditional fermented foods, indigenous dietary practices, and the health benefits of moderate microbial exposure. The regulatory landscape for microbiome-based therapeutics is evolving rapidly. Government agencies are developing new frameworks for evaluating the safety and efficacy of live bacterial treatments. These regulations must balance the need for safety and scientific rigor with the unique challenges of regulating living microorganisms that can evolve and adapt within the human body. Ethical considerations around microbiome medicine are also emerging. Questions about consent for microbiome analysis, privacy of microbial data, and equitable access to microbiome-based treatments will need to be addressed as these technologies become more widely available. The potential for microbiome enhancement raises questions about what constitutes optimal microbial health and whether people should seek to improve their microbiomes beyond what is necessary for basic health. These questions parallel broader debates about human enhancement and the goals of medical intervention. International collaboration in microbiome research is essential given the global nature of microbial ecosystems and human health. Large-scale studies involving diverse populations are needed to understand how microbiome health relationships vary across different genetic backgrounds, cultural practices, and environmental conditions. The American Gut Project, the Human Microbiome Project, and similar initiatives around the world are creating massive databases of microbial information that researchers can use to identify patterns and develop new treatments. These collaborative efforts are accelerating the pace of discovery and ensuring that benefits reach diverse populations. Training the next generation of healthcare providers to understand and apply microbiome science represents a crucial challenge. Medical schools are beginning to incorporate microbiome education into their curricula, but widespread adoption of microbiome-informed medical practice will require extensive continuing education for practicing physicians. The integration of microbiome analysis into routine healthcare is likely to happen gradually, beginning with specific applications where the evidence is strongest and expanding as our understanding grows. Early adopters may include gastroenterologists treating inflammatory bowel disease, psychiatrists exploring the gut-brain axis, and pediatricians focusing on early-life microbial development. As we look toward this future of microbial medicine, it's important to remember that we are still in the early stages of understanding these complex systems. The human microbiome contains thousands of species, millions of genes, and countless molecular interactions that scientists are only beginning to map and understand. The path forward will require continued research, careful clinical testing, thoughtful regulation, and ongoing attention to ethical considerations. But the potential benefits are enormous. More precise treatments with fewer side effects, prevention of diseases before they develop, and a deeper understanding of what it means to be optimally healthy. Tonight, as you rest, the microbes within your body continue their ancient work, unaware that they have become the subject of intense scientific study and medical innovation. They maintain their metabolic activities, communicate through chemical signals, and respond to the changing conditions within your body. These microscopic partners, which have shaped human evolution and continue to influence human health, may soon become active participants in a new era of medicine, a future where treatment is tailored not just to your human genetics, but to your microbial ecosystem, where prevention begins with understanding and optimizing the invisible world within you, where health is understood as the harmonious function of human and microbial communities working together. This future is not distant speculation, but an emerging reality, built on the foundation of scientific discoveries that reveal the profound interconnectedness of all life. As we continue to explore the invisible world inside us, we discover not just new ways to treat disease, but new ways to understand what it means to be human. Conclusion: embracing our microbial nature as our journey through the invisible world inside us draws to a close, we find ourselves forever changed by the knowledge of who we truly are. We are not solitary beings navigating an independent existence, but rather walking ecosystems, living worlds, universes of cooperation between human and microbial life. The 3 pounds of bacteria, viruses, fungi, and other microorganisms that share your body are not mere passengers or tenants. They are partners in the deepest sense, collaborators in the fundamental processes of life itself. They help digest your food, synthesize your vitamins, train your immune system, influence your mood, and shape your very identity in ways both subtle and profound. This partnership began before your first breath and will continue throughout your lifetime, evolving and adapting as you grow, age, and encounter new experiences. The bacteria that colonized your gut as an infant are different from those that live there today, and they will be different again tomorrow. You are in constant dialogue with the microbial world, constantly changing, constantly becoming. Understanding this microbial nature of human life changes everything. It changes how we think about health and disease, revealing that many conditions once thought to be purely human problems may actually be ecosystem disorders. It changes how we think about treatment, suggesting that healing may sometimes require restoring balance to our internal communities rather than simply targeting symptoms. It changes how we think about ourselves, revealing that the boundaries between self and other, between human and microbial, are far more fluid than we ever imagined. You are not just you, you are a collaborative masterpiece of evolution, a testament to the power of cooperation between different forms of life. The implications of this understanding extend far beyond medicine. They touch on fundamental questions about identity, consciousness, and our place in the natural world. If our thoughts and emotions can be influenced by bacterial metabolites, if our immune responses depend on microbial education, if our very survival requires ongoing cooperation with trillions of microscopic partners, what does this mean for our understanding of human nature? Perhaps it means that we have never been as separate from the natural world as we thought. The bacteria in your gut connect you to soil microbes, to the bacteria in fermented foods, to the microbial communities of every environment you encounter. You are part of a vast, interconnected web of microbial life that spans the globe. This perspective offers both humility and wonder. Humility in recognizing that human intelligence and capability emerge from collaboration with countless other organisms. Wonder in discovering the exquisite complexity and beauty of these microbial partnerships that make life possible. The choices you make each day, what you eat, how you manage stress, whether you spend time in nature, how you care for your sleep, all influence this internal ecosystem. You have the power to support the health and diversity of your microbial partners through conscious choices about how you live. Eating a diverse array of plant foods provides the fiber that feeds beneficial bacteria. Fermented foods introduce new microbial species and support existing communities. Time spent in natural environments exposes you to environmental microbes that can enhance your microbial diversity. Quality sleep supports the circadian rhythms that help maintain microbial balance. The medications you take, the stress you experience, the chemicals you encounter in your environment, all of these factors influence your microbial communities. Understanding these connections empowers you to make choices that support the health of your entire ecosystem. As we stand on the threshold of a new era in medicine and human understanding, we have the opportunity to embrace our microbial nature fully. This means moving beyond the adversarial relationship with bacteria that characterized much of modern medicine toward a more nuanced understanding of when microbes are helpful and when they may cause harm. It means recognizing that optimal health involves maintaining diverse, balanced microbial communities rather than trying to eliminate all bacteria from our lives. It means understanding that our individual health is connected to the health of microbial ecosystems in our environment, our food systems, and our communities. The future of human health may depend on our ability to care for these invisible partners that have supported life on Earth for billions of years. As we develop new technologies to analyze and manipulate microbial communities, we must do so with wisdom, recognizing both the tremendous potential benefits and the responsibility that comes with this power. The children being born today will grow up in a world where microbiome analysis is routine, where personalized probiotics are prescribed based on individual microbial profiles, where the health of gut bacteria is considered as important as the health of any organ. They will inherit both our scientific advances and the consequences of our choices about how we interact with the microbial world. Research continues to reveal new dimensions of our microbial partnerships. Scientists are discovering how skin bacteria protect against harmful UV radiation, how oral bacteria influence cardiovascular health, how bacteria in the lungs support respiratory function. Each new discovery reinforces the fundamental truth that human health and microbial health are inseparable. The practical applications of microbiome science will continue to expand, offering new possibilities for treating diseases that have long resisted conventional approaches. From depression to diabetes, from allergies to autoimmune diseases, understanding microbial contributions to these conditions opens new pathways for healing. But perhaps the most profound impact of microbiome science will be on our understanding of what it means to be human. We are not isolated individuals, but integrated ecosystems. We are not masters of our biological destiny, but partners in an ancient collaboration. We are not separate from nature, but expressions of the fundamental interconnectedness of all life. This understanding brings with it a sense of responsibility. The choices we make affect not just our own health, but the health of the microbial communities we carry. The antibiotics we take, the foods we eat, the environments we create all have consequences for these invisible partners that depend on us as much as we depend on them. It also brings a sense of connection. The bacteria in your gut are descendants of microbes that have lived with humans for thousands of generations. They carry within their genes the history of human migration, dietary adaptation, and environmental interaction. You are connected through these microbial lineages to every human who has ever lived. The care of your microbiome becomes an act of stewardship, a way of honoring the ancient partnerships that make your life possible. When you choose foods that support beneficial bacteria, when you avoid unnecessary antibiotics, when you manage stress and prioritize sleep, you are caring for communities of organisms that have co-evolved with humans for millennia. As you prepare for sleep tonight, take a moment to appreciate the remarkable universe that exists within you. The bacteria in your gut are processing the nutrients from your last meal, producing vitamins and metabolites that support your health. They are communicating with your immune system, helping to maintain the balance between protection and tolerance. They are sending signals to your brain that influence your mood, your sleep quality, and your dreams. These microscopic partners work tirelessly without recognition or reward. Their only goal the continuation of the ancient collaboration that binds human and microbial life together. They represent one of the most successful partnerships in the history of life on Earth, a testament to the power of cooperation over competition. In understanding our microbial nature, we discover that we are never truly alone. We carry within us a universe of life, a cosmos of cooperation, a world of wonder that continues its work whether we are conscious of it or not. We are walking ecosystems, living examples of the profound interconnectedness that characterizes all life on Earth. The invisible world inside us is no longer invisible to science, but it remains largely hidden from everyday awareness. As this knowledge becomes more widespread, as microbiome science moves from research laboratories to clinical practice to public consciousness, we have the opportunity to develop a new relationship with our microbial partners. This relationship, based on understanding rather than fear, on cooperation rather than conquest, may help us navigate the health challenges of the modern world while honoring the ancient wisdom encoded in microbial communities that have sustained life for billions of years. Tonight, as you rest, your microbiome continues its work. Bacteria divide and multiply, establishing new colonies and maintaining existing communities. Chemical messages flow between microbial species and between microbes and human cells. The complex dance of metabolism, immunity, and communication continues, supporting your health, your well-being, and your very existence. You are part of this dance, a willing participant in the ongoing collaboration between human and microbial life. Your choices matter. Your health affects the health of your microbial partners, and their well-being influences yours in return. In embracing our microbial nature, we discover not a diminishment of human uniqueness, but an enhancement of it. We are remarkable not despite our dependence on microbes, but because of it. We are the beneficiaries of billions of years of evolutionary innovation, the inheritors of partnerships that have been refined across countless generations. The story of the invisible world inside us is ultimately a story of cooperation, adaptation, and mutual support. It is a reminder that life, in all its magnificent complexity, emerges not from competition alone but from the willingness of different organisms to work together toward common goals. As we continue to explore this invisible world, as we develop new ways to support and enhance our microbial partnerships, we move toward a future where human health is understood in its full ecological context. A future where medicine works with natural systems rather than against them. A future where the health of individuals and the health of microbial communities are recognized as inseparable aspects of a larger whole. This is the promise of microbiome science, not just new treatments for disease, but a new understanding of health itself. Not just personalized medicine, but ecological medicine that recognizes the interconnectedness of all life. Not just human health, but planetary health, understood as the complex web of relationships that sustain life in all its forms. The invisible world inside us connects us to everything else that lives. The bacteria in your gut share genes with bacteria in soil, in oceans, in the air around us. The metabolic pathways that support your life are variations on themes that have been playing out in microbial communities for billions of years. In caring for our microbiomes, we participate in the larger project of caring for life itself. In understanding our microbial partnerships, we gain insight into the fundamental principles that organize living systems everywhere. In embracing our role as ecosystems, we discover our true place in the community of life that spans the earth. The journey into the invisible world inside us reveals that there is no true boundary between inner and outer, between self and environment, between human and microbial. We are expressions of the same creative processes that have shaped life since its earliest emergence, participants in the same ongoing experiment in cooperation that continues to generate new forms of beauty and complexity. Tonight, as you drift towards sleep, you carry within you the legacy of this ancient partnership. The bacteria in your body connect you to the earliest forms of life on Earth and to the future possibilities of human and microbial coevolution. You are a living bridge between past and future, a current expression of the endless creativity of life itself. Rest well, knowing that you are never alone, never separate from the vast community of life that sustains and surrounds you. The invisible world inside you continues its patient work, maintaining the conditions that make your consciousness, your dreams, and your tomorrows possible. You are home to trillions of partners in the magnificent adventure of being alive. This is their gift to you, and your gift to them, the continuation of the ancient dance between human and microbial life, the ongoing collaboration that makes everything else possible. In the quiet of the night, as your breathing slows and your mind settles toward rest, the invisible world inside you persists in its essential work. These microscopic partners, invisible to the naked eye but visible now to science and to understanding, continue the processes that have sustained life for eons and will continue long after our individual stories have ended. We are part of something larger than ourselves, participants in a story that began billions of years ago and continues in every breath, every heartbeat, every moment of existence. The invisible world inside us is not separate from the visible world around us. They are one seamless reality, one interconnected whole, one magnificent expression of the creative power of life itself. This is who you are, not a single organism but a universe, not an individual but an ecosystem, not separate but connected to everything that has ever lived or ever will live. The invisible world inside you is visible now, and in seeing it, we see ourselves truly for the first time. Sleep well, living universe. Rest peacefully, walking ecosystem. Dream deeply, community of life. Tomorrow awaits, and your microbial partners will be there to greet it with you, as they have been since the very beginning, as they will be until the very end. The invisible world inside us is invisible no more. Mind, body, and microbes in the gentle darkness of evening, as your mind begins to settle and your body prepares for rest. An extraordinary conversation is taking place deep within you. It is a dialogue between your brain and your gut, mediated by trillions of microscopic partners whose influence on your thoughts, emotions, and well-being is only now beginning to be understood. This conversation has been happening every moment of your life, shaping your moods, influencing your decisions, and contributing to your mental health in ways that would have seemed impossible just decades ago. Tonight, as you listen to these words, we invite you to explore the remarkable connections between mind, body, and the microbial communities that live within you. The story we are about to tell will change how you think about consciousness itself, revealing that the boundaries between your thoughts and the microscopic life in your gut are far more fluid than anyone ever imagined. It is a story of partnership, of ancient alliances, and of discoveries that are revolutionizing our understanding of what it means to be human. The gut-brain axis deep within your abdomen, in the winding passages of your intestines, lives what scientists have come to call your second brain. This enteric nervous system contains more than 500 million neurons, more nerve cells than exist in your spinal cord, all dedicated to the complex task of managing your digestive system and communicating with the brain in your head. But this second brain does not work alone. It is in constant dialogue with the trillions of bacteria that call your gut home, and together they form one of the most sophisticated communication networks in the biological world. Every thought you think, every emotion you feel, every decision you make is influenced by this ongoing conversation between your mind and your microbes. The discovery of this gut-brain axis has transformed our understanding of mental health, revealing that conditions like depression, anxiety, and even autism may not be purely neurological disorders, but ecosystem imbalances that extend throughout the body. Your gut bacteria are not passive residents but active participants in your mental and emotional life. Consider the remarkable story of Thomas, a successful architect in his early 40s who had struggled with treatment-resistant depression for over a decade. Despite trying numerous medications and therapies, Thomas found himself trapped in cycles of despair that seemed to have no clear cause or cure. His days were clouded by persistent sadness, his energy was depleted, and his once sharp mind felt foggy and disconnected. Thomas had given up hope of finding relief when he learned about emerging research connecting gut health to mental health. Skeptical but desperate, he agreed to participate in a clinical trial studying the effects of targeted microbiome interventions on depression. Comprehensive testing revealed that his gut microbiome was severely depleted, lacking many of the bacterial species known to produce neurotransmitters and anti-inflammatory compounds. The treatment protocol was unlike anything Thomas had experienced before. Instead of focusing solely on brain chemistry, the approach targeted his entire gut ecosystem. He began taking carefully selected probiotic strains known to support mental health, modified his diet to feed beneficial bacteria, and incorporated fermented foods that introduced new microbial species to his gut. The changes were gradual but profound. Over the course of 6 months, as Thomas's gut microbiome regained its diversity and balance, the fog that had clouded his mind began to lift. His energy returned, his mood stabilized, and for the first time in years he felt like himself again. Blood tests showed reduced inflammatory markers. An analysis of his gut bacteria revealed a flourishing ecosystem of beneficial species. Thomas's recovery illustrates a fundamental shift in how we understand mental health. The brain that thinks your thoughts and feels your emotions is not isolated from the rest of your body, but is in constant communication with the microbial communities in your gut. This communication happens through multiple pathways. The vagus nerve that directly connects gut to brain, the immune system that responds to bacterial signals, and the bloodstream that carries bacterial metabolites throughout your body. Dr. John Cryan, a leading neuroscientist at University College Cork, has spent years mapping these connections between gut bacteria and brain function. His research has revealed that certain bacterial species can directly influence mood, anxiety, and cognitive function through their production of neurotransmitters and other bioactive compounds. The most striking example of this microbial influence on mental health involves serotonin, often called the happiness neurotransmitter. While most people associate serotonin with the brain, approximately 90% of your body's serotonin is actually produced in your gut, and much of this production is influenced by gut bacteria. Certain species of bacteria, particularly those in the Enterococcus and Streptococcus families, can directly synthesize serotonin from dietary tryptophan. Other bacteria influence serotonin production by gut cells themselves, essentially acting as regulators of this crucial neurotransmitter. When these bacteria are depleted or imbalanced, serotonin production can be disrupted, potentially contributing to depression, anxiety, and sleep disorders. The case of Maria illustrates this connection beautifully. A graduate student studying literature, Maria had always been known for her even temperament and optimistic outlook. But following a severe bout of food poisoning that required treatment with powerful antibiotics, she found herself struggling with anxiety and mood swings that seemed to come from nowhere. The antibiotics had eliminated the harmful bacteria causing her illness, but they had also devastated the beneficial bacteria in her gut, including species responsible for serotonin production. As her gut microbiome slowly recovered over months, her mental health gradually stabilized, but it never quite returned to its pre-illness state. Working with a psychiatrist who understood the gut-brain connection, Maria began a targeted program to restore the specific bacterial species involved in neurotransmitter production. She introduced fermented foods rich in serotonin-producing bacteria, took targeted probiotics, and modified her diet to support microbial diversity. Over time, as her gut ecosystem regained its complexity, her mental resilience returned. The production of other neurotransmitters by gut bacteria is equally important for mental health. GABA, the brain's primary calming neurotransmitter, is produced by several bacterial species, including certain strains of lactobacillus. People with anxiety disorders often show reduced levels of GABA-producing bacteria in their gut microbiomes. Dopamine, crucial for motivation and reward processing, is also produced by gut bacteria. The balance of dopamine-producing and dopamine-consuming bacteria in the gut may influence everything from addiction susceptibility to attention and focus. This helps explain why gut health problems are often accompanied by changes in motivation and cognitive function. Dr. Imran Mayer, a gastroenterologist and neuroscientist at UCLA, describes the gut-brain axis as a bidirectional highway of communication. Stress and emotions can alter gut bacteria composition, while changes in gut bacteria can influence mood and behavior. This creates feedback loops that can either support mental health or contribute to psychological distress. The research on autism spectrum disorders has provided some of the most compelling evidence for the gut-brain connection. Children with autism often show distinct patterns of gut bacteria composition, with reduced diversity and altered ratios of different bacterial families. While the relationship between gut bacteria and autism is still being studied, early intervention trials targeting the microbiome have shown promising results. 8-year-old Jake had been diagnosed with autism spectrum disorder at age 3. His parents had tried various therapies with limited success when they learned about research connecting gut health to autism symptoms. Comprehensive analysis revealed that Jake's gut microbiome was severely imbalanced, with an overgrowth of potentially harmful bacteria and a lack of beneficial species. Working with specialists who understood the microbiome connection, Jake's parents implemented a careful protocol involving dietary changes, targeted probiotics, and gradual introduction of fermented foods. Over 18 months, as Jake's gut microbiome became more diverse and balanced, his parents noticed improvements in his communication, social interaction, and sensory sensitivities. While Jake's autism did not disappear, the quality of his life improved significantly. He began making eye contact more readily, his language skills developed, and his extreme reactions to certain stimuli decreased. The changes correlated directly with improvements in his gut bacteria diversity, suggesting that his brain function was indeed influenced by his microbial partners. The inflammatory connection between gut and brain represents another crucial aspect of the gut-brain axis. Chronic inflammation in the brain has been implicated in depression, anxiety, cognitive decline, and neurodegenerative diseases. Much of this inflammation may originate in the gut, where imbalanced bacteria can produce inflammatory compounds that travel to the brain. When the gut barrier becomes compromised, a condition sometimes called leaky gut, bacterial toxins can enter the bloodstream and trigger inflammatory responses throughout the body, including in the brain. This neuroinflammation can interfere with neurotransmitter production, disrupt neural connections, and contribute to mood disorders. Conversely, beneficial gut bacteria produce anti-inflammatory compounds that can protect the brain from harmful inflammation. Short-chain fatty acids, produced when bacteria ferment dietary fiber, have particularly potent anti-inflammatory effects in neural tissue. These molecules can cross the blood-brain barrier and directly influence brain function. The timing of gut microbiome development appears to be crucial for long-term mental health. The first few years of life represent a critical window during which gut bacteria help train the developing brain and establish patterns of gut-brain communication that may persist throughout life. Children who experience significant disruptions to their gut microbiome during this critical period, perhaps through antibiotic use or other factors, may be at increased risk for mental health problems later in life. This has led researchers to pay increased attention to protecting and supporting healthy microbiome development in early childhood. The influence of gut bacteria on sleep represents another important aspect of the gut-brain connection. Many of the neurotransmitters involved in sleep regulation, including serotonin and GABA, are produced or influenced by gut bacteria. People with disrupted gut microbiomes often experience sleep disturbances, while improving gut health frequently leads to better sleep quality. The circadian rhythms that regulate sleep-wake cycles also influence gut bacteria activity. Your microbes have their own daily rhythms that affect their metabolism and neurotransmitter production. Disruptions to these microbial circadian rhythms, from shift work or jet lag, can affect both gut health and sleep quality. Stress represents both a cause and consequence of gut-brain axis dysfunction. Chronic stress can alter gut bacteria composition, reducing beneficial species and promoting the growth of potentially harmful ones. At the same time, an imbalanced gut microbiome can increase stress sensitivity and reduce resilience to psychological challenges. The case of David, a high-pressure executive, illustrates this stress microbiome cycle. Years of chronic work stress had gradually altered his gut bacteria composition, reducing diversity and promoting inflammatory species. This microbial imbalance contributed to anxiety, sleep problems, and digestive issues that further increased his stress levels. Breaking this cycle required addressing both stress management and gut health simultaneously. David learned stress reduction techniques, while also working to restore his gut microbiome through dietary changes and targeted probiotics. As his gut health improved, his stress resilience increased, creating a positive feedback loop that supported both his mental and physical well-being. The personalized nature of gut-brain interactions means that mental health interventions may need to be tailored to individual microbiome profiles. What works for one person may not work for another, depending on their unique bacterial composition and metabolic capabilities. Researchers are developing diagnostic tools that can analyze gut bacteria composition and predict which interventions are most likely to be effective for specific individuals. This personalized approach to mental health, based on understanding each person's unique gut-brain axis, represents the future of psychiatric treatment. The therapeutic applications of gut-brain axis research are expanding rapidly. Psychobiotics, probiotic preparations specifically designed to support mental health, are showing promise in clinical trials for depression, anxiety, and other mood disorders. These living medications work by introducing beneficial bacteria that can produce neurotransmitters and reduce inflammation. Dietary interventions targeting the gut-brain axis are also proving effective. The Mediterranean diet, rich in fiber and fermented foods, has been associated with reduced depression risk and better cognitive function. Elimination diets that remove inflammatory foods while promoting beneficial bacteria growth have helped many people with treatment-resistant mental health conditions. As you rest tonight, the conversation between your gut and brain continues. Bacterial metabolites produced during the digestion of your evening meal travel through your bloodstream to your brain, where they may influence the quality of your dreams. Neurotransmitters manufactured by gut bacteria help regulate your sleep cycles and prepare your mind for restoration. This ancient dialogue between mind and microbes has been shaped by millions of years of evolution, creating communication pathways so sophisticated that we are only beginning to understand their complexity. Your thoughts, emotions, and mental well-being emerge not from your brain alone, but from the collaborative effort of human and microbial intelligence working together. Immunity and inflammation. In the quiet depths of your body, a sophisticated education system operates around the clock, training the defenders that keep you healthy and alive. Your immune system, with its billions of specialized cells, does not emerge fully formed knowing friend from foe. Instead, it learns through careful instruction from trillions of microbial teachers that have been shaping human immunity for millennia. This education begins before your first breath and continues throughout your lifetime, with gut bacteria serving as the primary instructors in a curriculum that determines whether your immune system will respond appropriately to threats or turn against your own body in autoimmune confusion. The relationship between your microbiome and immune system represents one of the most elegant examples of biological cooperation on Earth. From the moment bacteria first colonize your gut in infancy, they begin the delicate process of teaching your immune cells when to fight, when to tolerate, and when to heal. Consider the story of Elena, born into a family with a strong history of autoimmune disease. Her grandmother had rheumatoid arthritis, her mother struggled with inflammatory bowel disease, and Elena seemed destined to follow a similar path. By age 12, she was already showing early signs of Crohn's disease, with recurring abdominal pain and inflammatory markers in her blood tests. Elena's gastroenterologist, Dr. Sarah Chen, had been following research on the connection between gut bacteria and autoimmune disease. Comprehensive analysis of Elena's gut microbiome revealed what Dr. Chen suspected: a severely imbalanced bacterial ecosystem with reduced diversity and an overgrowth of inflammatory species. Traditional treatment would have focused on suppressing Elena's immune system with powerful medications. Instead, Dr. Chen proposed a different approach, one that aimed to restore balance to Elena's gut ecosystem and retrain her immune system through microbial intervention. The treatment protocol was comprehensive and gradual. Elena began eating a carefully designed diet rich in fiber and fermented foods to feed beneficial bacteria. She took targeted probiotics containing bacterial strains known to support immune tolerance. Most importantly, the family made lifestyle changes to support microbial diversity, including time spent in natural environments and reduced use of antimicrobial products. Over 2 years, Elena's gut microbiome gradually transformed. Beneficial bacteria species that had been nearly absent began to flourish. Inflammatory markers in her blood decreased. Most remarkably, her Crohn's symptoms disappeared entirely, and follow-up colonoscopies showed complete healing of her intestinal inflammation. Elena's recovery illustrates the profound influence that gut bacteria have on immune function. These microscopic teachers work by presenting their molecular signatures to immune cells in controlled amounts, like showing flashcards to students. This early education helps establish immune memory and teaches the system to distinguish between harmless substances and genuine threats. The process begins in specialized areas of the gut called Peyer's patches, where immune cells constantly sample bacterial products from the intestinal environment. Dendritic cells, which serve as the immune system's intelligence officers, examine these bacterial signatures and decide whether to mount an immune response or maintain peaceful coexistence. Beneficial bacteria have evolved sophisticated ways to communicate their peaceful intentions to immune cells. They produce metabolites that suppress excessive inflammation while maintaining protective responses against genuine pathogens. They strengthen the gut barrier that separates bacterial communities from immune cells, preventing unnecessary alarms. They even influence the development of regulatory T cells, specialized immune cells that prevent autoimmune reactions. Dr. Yasmine Belkade, an immunologist at the National Institutes of Health, has spent years studying how commensal bacteria shape immune function. Her research has revealed that these beneficial microbes don't just coexist with our immune system, they actively participate in immune responses and help maintain the delicate balance between protection and tolerance. When this microbial education system fails, the consequences can be devastating. Children born by cesarean section or treated with antibiotics in early life sometimes miss crucial lessons in the microbial curriculum. Without proper immune education from diverse gut bacteria, they may develop immune systems that overreact to harmless substances, leading to allergies and asthma, or underreact to genuine threats, increasing infection risk. The hygiene hypothesis, first proposed by epidemiologist David Strachan, suggests that some exposure to microbes during early life is necessary for proper immune development. While cleanliness is important for preventing infectious diseases, an overly sterile environment may deprive the developing immune system of the microbial teachers it needs to function optimally. This principle is beautifully illustrated by studies of Amish communities in Pennsylvania. Children raised in these traditional farming communities, with extensive animal contact and limited antibiotic use, show dramatically lower rates of allergies and autoimmune diseases compared to their urban counterparts. Their immune systems, educated by diverse environmental bacteria, develop what researchers call old-school immunity, robust, well-calibrated, and resistant to inflammatory overreactions. Dr. Mark Holbry, an allergist who has studied Amish communities for years, describes their children's immune profiles as remarkably resilient. These children's immune systems learned from a diverse faculty of microbial teachers, he explains. Their bacteria taught them wisdom that urban children often miss. The production of immunoglobulin A, or IgA, represents one of the most direct examples of how gut bacteria support immune function. IgA is the most abundant antibody in the human body, coating mucosal surfaces throughout the gut, lungs, mouth, and other areas where microbes are likely to be encountered. The production of IgA is heavily influenced by gut bacteria, which stimulate immune cells to produce this protective antibody. People with depleted gut microbiomes often have reduced IgA production, making them more susceptible to infections and inflammatory diseases. Conversely, those with diverse, healthy microbiomes typically have robust IgA responses that help maintain immune homeostasis throughout the body. The case of Michael, a young boy with recurrent respiratory infections, illustrates this connection. Despite multiple rounds of antibiotics, Michael continued to develop pneumonia and bronchitis every few months, suggesting an underlying immune dysfunction. Analysis revealed that his gut microbiome had been severely depleted by repeated antibiotic treatments, and his IgA levels were well below normal. Rather than prescribing more antibiotics, Michael's pediatrician focused on restoring his gut microbiome diversity. Through targeted probiotics, fermented foods, and dietary changes, Michael's bacterial ecosystem gradually recovered. As beneficial bacteria re-established themselves, his IgA production increased, and his susceptibility to respiratory infections decreased dramatically. The inflammatory balance maintained by gut bacteria is crucial for preventing autoimmune diseases like type 1 diabetes, multiple sclerosis, and inflammatory bowel disease. These conditions arise when the immune system mistakenly attacks the body's own tissues, often in the context of chronic inflammation that beneficial bacteria normally help prevent. Short-chain fatty acids produced by bacterial fermentation of dietary fiber have particularly potent anti-inflammatory effects. These molecules can directly influence immune cell function, promoting the development of regulatory T cells that help maintain immune tolerance. They also strengthen the gut barrier, reducing the translocation of inflammatory bacterial products into systemic circulation. The loss of fiber-fermenting bacteria in modern populations may contribute to the increased incidence of autoimmune diseases in developed countries. The Western diet, low in fiber and high in processed foods, often fails to support the bacteria that produce these protective compounds. Research has shown that people with type 1 diabetes often have altered gut microbiome compositions, with reduced levels of beneficial bacteria and increased inflammatory species. While type 1 diabetes is primarily a genetic condition, the timing of its onset may be influenced by environmental factors, including gut bacteria composition. Studies of children at high genetic risk for type 1 diabetes have found that those who develop the disease often show changes in their gut microbiome months or even years before symptoms appear. This suggests that microbial factors may play a role in triggering autoimmune destruction of insulin-producing cells. The connection between gut bacteria and inflammatory bowel diseases like Crohn's disease and ulcerative colitis is even more direct. These conditions involve chronic inflammation of the intestinal tract, often in the context of an inappropriate immune response to normal gut bacteria. People with IBD typically show reduced microbial diversity and altered bacterial compositions, with an overgrowth of potentially inflammatory species and a loss of protective bacteria. While genetic factors predispose some people to these conditions, Environmental triggers, including changes in gut bacteria, appear to play a crucial role in disease development. Treatment approaches that target the microbiome, including dietary interventions, probiotics, and even fecal microbiota transplantation, have shown promise for managing inflammatory bowel disease. By restoring bacterial balance and reducing inflammation, these approaches can sometimes achieve remission even in severe cases. The seasonal patterns of autoimmune disease symptoms also reflect the gut-immune connection. Many people with conditions like rheumatoid arthritis or multiple sclerosis notice that their symptoms worsen during certain times of year, often corresponding to periods when gut microbiome diversity naturally decreases due to dietary changes or reduced environmental microbial exposure. Stress represents another important factor in the microbiome-immunity relationship. Chronic stress can alter gut bacteria composition while simultaneously suppressing immune function, creating vulnerability to both infections and autoimmune diseases. The stress hormones cortisol and adrenaline can directly influence bacterial growth and metabolism, favoring some species over others. Conversely, beneficial gut bacteria can influence stress resilience through their effects on the immune system. Some bacteria produce compounds that can reduce systemic inflammation and support healthy stress responses, creating feedback loops that either support overall health or contribute to disease. The aging process also transforms the microbiome-immune relationship. As we age, our gut microbiome typically becomes less diverse, and our immune system may become less responsive to microbial signals. This immunosenescence can contribute to increased susceptibility to infections and chronic inflammatory diseases in older adults. However, maintaining a diverse gut microbiome through appropriate diet, exercise, and lifestyle choices may help preserve immune function with aging. Studies of centenarians have found that people who live to 100 and beyond often maintain surprisingly diverse gut microbiomes, suggesting that microbial diversity may be one factor contributing to healthy longevity. The therapeutic potential of understanding microbiome-immune interactions is enormous. Researchers are developing new treatments based on modulating this relationship, from precision probiotics designed to enhance immune responses to specific diseases to microbiome-targeted therapies for autoimmune conditions. Vaccine effectiveness also appears to be influenced by gut microbiome composition. People with more diverse gut microbiomes often develop stronger antibody responses to vaccinations, while those with depleted microbiomes may have reduced vaccine efficacy. This has led to research on probiotic supplements that could enhance vaccine responses, particularly in vulnerable populations like the elderly. The concept of trained immunity, where immune cells develop enhanced responses through exposure to certain microbes, represents another frontier in microbiome immune research. Beneficial bacteria may help train immune cells to respond more effectively to future threats, providing broader protection than traditional vaccines. As you prepare for sleep tonight, your immune system continues its vigilant patrol, guided by lessons learned from countless microbial teachers. These microscopic instructors have shaped your body's defenses through millions of years of evolutionary partnership, creating an immune system that is uniquely yours yet connected to the ancient wisdom of the microbial world. The education never stops. Every meal you eat, every environment you encounter, every choice you make about antibiotics or stress management influences the ongoing dialogue between your immune system and your microbial partners. They work together in the darkness, maintaining the delicate balance that keeps you healthy, protected, and alive. Microbes and lifestyle. In the gentle rhythm of your daily life, From the foods you choose to eat to the environments you inhabit, you are constantly shaping and reshaping the microbial universe within you. Every decision you make, every habit you maintain, every aspect of your modern lifestyle sends ripples through the trillions of microorganisms that call your body home. The relationship between lifestyle and microbiome is not one way. Just as your choices influence your bacterial partners, these microscopic communities influence your preferences, your health, and even your behavior in return. Understanding this dynamic partnership offers profound insights into how we might live in greater harmony with the invisible ecosystems that sustain us. The story of modern lifestyle's impact on our microbial partners begins with perhaps the most fundamental aspect of daily life: what we choose to eat. The transformation of human diets over the past century represents one of the most dramatic environmental changes our gut bacteria have ever encountered, and the consequences of this shift are still unfolding. Consider the remarkable case of Dr. Timothy Spector, a genetic epidemiologist at King's College London, who decided to use his own son as a subject in an unusual experiment. The younger Spector, then a college student, agreed to eat nothing but McDonald's food for 10 days as part of a research project examining how rapid dietary changes affect the gut microbiome. The results were shocking. Within just 4 days of starting the fast food diet, the young man had lost nearly 40% of his gut bacterial diversity. Species that had taken years to establish in his gut ecosystem disappeared entirely, replaced by a much simpler, less resilient microbial community. When he returned to his normal, varied diet, some bacterial species recovered, but others never returned. This experiment, though extreme, illustrates the profound sensitivity of our gut bacteria to dietary changes. The foods we eat don't just nourish us, they determine which bacterial species thrive, which ones struggle, and which ones disappear entirely from our internal ecosystems. The Western diet, characterized by high levels of processed foods, refined sugars, and low fiber content, creates an environment that favors certain bacterial species while starving others. Processed foods often contain preservatives and additives that can directly harm beneficial bacteria. The lack of fiber in many modern diets deprives beneficial bacteria of their primary food source, causing their populations to dwindle. Dr. Justin Sonnenberg, a microbiologist at Stanford University, has spent years studying how dietary fiber affects gut bacteria. His research has shown that fiber-fermenting bacteria are among the most important members of our gut ecosystem, producing short-chain fatty acids that support gut barrier function, reduce inflammation, and even influence brain health. When people switch from high-fiber to low-fiber diets, these beneficial bacteria begin to starve within days. Some species may go dormant, waiting for fiber to return. Others may be lost entirely, particularly if the low-fiber diet continues for extended periods. This loss of diversity can have cascading effects throughout the gut ecosystem. The Mediterranean diet, in contrast, provides an environment where diverse bacterial communities can flourish. Rich in fiber from fruits, vegetables, and whole grains, abundant in fermented foods like yogurt and aged cheeses, and featuring healthy fats from olive oil and fish, this traditional eating pattern supports microbial diversity in multiple ways. Studies comparing people following Mediterranean-style diets to those eating typical Western diets consistently show differences in gut microbiome composition. Mediterranean diet followers tend to have higher levels of beneficial bacteria, greater overall diversity, and reduced markers of inflammation. Maria Gonzalez, a nutritionist working in Barcelona, has observed these differences firsthand in her practice. Clients who grew up eating traditional Spanish foods with plenty of vegetables, legumes, olive oil, and fermented foods typically show robust gut microbiome diversity when tested. Those who have adopted more processed, Western-style diets often have simplified bacterial ecosystems and more inflammatory health markers. The role of fermented foods in supporting gut health represents one of humanity's oldest biotechnologies. For thousands of years, cultures around the world have developed techniques for fermenting foods, not just to preserve them but also to enhance their nutritional value and introduce beneficial bacteria into the diet. Kimchi from Korea, kefir from the Caucasus, kombucha from China, sauerkraut from Germany, yogurt from the Middle East. These traditional fermented foods serve as delivery systems for beneficial bacteria, while also providing the nutrients these microbes need to thrive in the gut. Dr. Erika Sonnenberg, working alongside her husband Justin at Stanford, has studied how fermented foods affect gut microbiome diversity. Their research has shown that people who regularly consume fermented foods tend to have more diverse gut microbiomes and better immune function, compared to those whose diets lack these traditional preparations. The case of Hiroshi, a Japanese businessman living in New York, illustrates the power of fermented foods to restore microbial health. After years of eating a typical American diet, Hiroshi began experiencing digestive problems and frequent illnesses that he had never had while living in Japan. Analysis of his gut microbiome revealed significantly reduced diversity compared to people following traditional Japanese diets. Working with a nutritionist familiar with microbiome science, Hiroshi began reintroducing traditional Japanese fermented foods into his diet: miso soup, natto, pickled vegetables, and fermented fish. Over 6 months, his gut microbiome diversity increased dramatically, his digestive symptoms resolved, and his overall health and energy improved. The impact of antibiotics on gut microbiome represents one of the most significant challenges to microbial health in modern life. While these medications have saved countless lives by treating serious infections, their broad-spectrum effects can devastate beneficial bacteria along with harmful pathogens. Each course of antibiotics is like a forest fire sweeping through the gut ecosystem, clearing established bacterial communities and leaving vacant niches for opportunistic species to colonize. Some beneficial bacteria may never return after antibiotic treatment, leading to permanently altered gut ecosystems. Dr. Martin Blaser's research at Rutgers University has shown that children who receive multiple courses of antibiotics early in life often develop simplified gut microbiomes that persist into adulthood. This early life microbial depletion may contribute to increased rates of allergies, asthma, and obesity in developed countries. The overuse of antibiotics in both human medicine and agriculture has created what some researchers call a microbiome crisis. In developed countries, the average person receives multiple courses of antibiotics during childhood and continues to receive them throughout life, often for conditions that might resolve without treatment. However, the judicious use of antibiotics when truly needed remains important for treating serious infections. The key is finding balance using these powerful medications when necessary, while taking steps to protect and restore beneficial bacteria. Some healthcare providers now recommend probiotic supplements during and after antibiotic treatment to help restore gut microbiome diversity. Others suggest increasing fiber intake and fermented foods to support the recovery of beneficial bacteria. Research is ongoing into more sophisticated approaches, including banking an individual's own gut bacteria before antibiotic treatment and reintroducing them afterward. The modern obsession with cleanliness and antimicrobial products also affects our microbial partnerships. While basic hygiene is important for preventing infectious diseases, the overuse of antibacterial soaps, hand sanitizers, and cleaning products may reduce beneficial microbial exposures that support immune development and overall health. Children raised in overly sterile environments may miss crucial microbial exposures during critical developmental periods. The hygiene hypothesis suggests that some exposure to microbes early in life is necessary for proper immune system development and long-term health. This principle is beautifully illustrated by studies of children raised on traditional farms compared to those in urban environments. Farm children, with their exposure to diverse animal and soil bacteria, typically develop more robust immune systems and lower rates of allergic diseases. The Amish communities of Pennsylvania provide a particularly striking example. Children in these communities, raised with extensive animal contact and limited use of antibiotics or antimicrobial products, show dramatically lower rates of asthma and allergies compared to their urban counterparts. Their immune systems, educated by diverse environmental bacteria, develop greater resilience and better regulatory mechanisms. Stress represents another crucial lifestyle factor affecting gut microbiome health. Chronic stress can alter bacterial composition through its effects on gut motility, immune function, and hormone production. The stress hormones cortisol and adrenaline can directly influence which bacterial species thrive and which ones struggle. People experiencing chronic stress often show reduced gut microbiome diversity and increased levels of potentially inflammatory bacteria. This creates a feedback loop where stress alters the microbiome, and the altered microbiome increases stress sensitivity through its effects on neurotransmitter production and inflammation. Sleep quality also influences microbial health. The circadian rhythms that regulate sleep-wake cycles affect bacterial activity and metabolism. Disrupted sleep patterns can alter gut bacteria composition, while poor gut health can interfere with sleep quality. Shift workers and frequent travelers often show alterations in their gut microbiomes that parallel their disrupted sleep patterns. Exercise represents one of the most powerful lifestyle interventions for supporting gut microbiome health. Regular physical activity increases microbial diversity, promotes the growth of beneficial bacteria, and enhances the production of short-chain fatty acids that support gut barrier function. Athletes often show distinct gut microbiome profiles compared to sedentary individuals, with higher levels of bacteria associated with anti-inflammatory effects and better metabolic health. Even moderate exercise, such as regular walking, can positively influence gut bacteria composition within weeks of starting a new routine. The environment we live in also shapes our microbial partners. Urban environments tend to have less microbial diversity than rural settings, and people living in cities often have less diverse gut microbiomes. Time spent in natural environments, forests, parks, gardens can increase microbial exposures that support gut health. Indoor air quality affects the bacteria we breathe and swallow throughout the day. Homes with good ventilation and connection to outdoor environments tend to harbor more diverse microbial communities than sealed, air-conditioned spaces. The bacteria living in your home environment contribute to your personal microbiome through constant, low-level exposure. Pet ownership also influences human microbiome diversity. Dogs and cats introduce bacterial species from the outdoor environment into homes, and children raised with pets often develop more diverse gut microbiomes. The bacteria from furry companions may help educate developing immune systems and support overall microbial health. Indigenous communities around the world provide valuable insights into how traditional lifestyles support microbial diversity. The Hadza people of Tanzania, one of the last remaining hunter-gatherer societies, show remarkable gut microbiome diversity that far exceeds that found in industrialized populations. The Hadza diet varies seasonally with available foods, including wild tubers, fruits, honey, and occasional meat. This dietary diversity, combined with constant exposure to environmental bacteria and minimal use of antibiotics or processed foods, maintains bacterial ecosystems that may represent the ancestral human microbiome. Similarly, rural populations in developing countries often show greater gut microbiome diversity than urban populations in developed countries. Children in rural areas of Africa, Asia, and South America typically have bacterial compositions that are more diverse and more similar to those found in other mammals than the simplified microbiomes common in industrialized societies. However, as these populations adopt Western lifestyles and diets, their microbial diversity often decreases within a single generation. This represents a potential loss of bacterial species that evolved with humans over millennia and may be crucial for optimal health. The concept of microbiome refugees beneficial bacteria that have been lost from industrialized populations but persist in traditional communities has emerged as researchers recognize that some bacterial species may be going extinct in human populations. These communities may serve as reservoirs of microbial diversity that could be crucial for understanding and treating diseases common in developed countries. Efforts to preserve and study traditional microbiomes are underway, including projects to catalog bacterial species from indigenous communities before they are lost to modernization. This research may help identify beneficial bacteria that could be reintroduced to populations that have lost them. The restoration of gut microbiome diversity through lifestyle changes is possible, though it requires sustained effort and patience. The bacterial communities in your gut are remarkably adaptable, responding to dietary and lifestyle modifications within days or weeks. However, rebuilding a truly diverse and resilient ecosystem may take months or years, particularly if the microbiome has been severely depleted. The story of Rebecca, a marketing executive in her 30s, illustrates both the challenges and possibilities of microbiome restoration. After years of high-stress work, frequent travel, and reliance on processed foods and antibiotics, Rebecca found herself struggling with digestive issues, frequent illnesses, and persistent fatigue. Analysis of her gut microbiome revealed dramatically reduced diversity, with several beneficial bacterial families nearly absent. Rebecca's path to restoration began with gradual dietary changes. She started incorporating more fiber-rich foods, including a variety of fruits, vegetables, and whole grains. She introduced fermented foods slowly, beginning with yogurt and kefir, before adding more diverse options like kimchi and kombucha. She reduced her consumption of processed foods and began cooking more meals at home. The changes weren't immediate, and Rebecca experienced some initial digestive discomfort as her gut bacteria adjusted to the new dietary environment. But over 6 months, her symptoms gradually improved. Follow-up testing showed significant increases in bacterial diversity, with the return of several beneficial species that had been nearly undetectable in her initial analysis. Perhaps most importantly, Rebecca learned to view her daily choices through the lens of their impact on her microbial partners. Each meal became an opportunity to feed beneficial bacteria. Stress management became important not just for her mental health, but for her gut health. Even her choice of cleaning products shifted toward less antimicrobial options that wouldn't unnecessarily disrupt her family's microbial environment. The seasonal nature of microbiome health offers another perspective on lifestyle and microbial wellness. Just as natural ecosystems change with the seasons, our gut microbiomes show seasonal variations that reflect changes in diet, activity levels, and environmental exposures. In traditional societies, these seasonal changes in microbiome composition were natural and healthy, reflecting the availability of different foods throughout the year and varying levels of physical activity. Winter might bring preserved and fermented foods that supported different bacterial communities than the fresh fruits and vegetables of summer. Modern life has largely disconnected us from these natural rhythms. With the same processed foods available year-round and consistent indoor environments that shield us from seasonal environmental bacteria, reconnecting with seasonal eating patterns and spending time outdoors throughout the year may help restore natural microbiome rhythms that support overall health. The social aspects of microbiome health are equally fascinating. Family members and people who live together tend to have more similar gut microbiomes than unrelated individuals living apart. This microbial sharing happens through countless small exposures, shared meals, physical contact, breathing the same air, and living in the same microbial environment. Children's microbiomes are particularly influenced by their family environment. They acquire bacteria from parents, siblings, and pets through daily interactions. The bacterial composition of household surfaces, influenced by cooking practices, cleaning habits, and the outdoor environment, also affects family microbiome composition. This social aspect of microbiome health suggests that efforts to improve gut health might be most successful when undertaken as a family or community endeavor. When everyone in a household adopts microbiome-supporting practices, the shared environment reinforces these positive changes. The role of cooking and food preparation in shaping microbiome health extends beyond just the ingredients used. Traditional cooking methods, including fermentation, sprouting, and slow cooking, can enhance the microbial content and digestibility of foods. Home-cooked meals, even when made with simple ingredients, tend to support greater microbiome diversity than restaurant or processed foods. The act of gardening represents another powerful way to increase beneficial microbial exposures while also providing fresh, fiber-rich foods. Soil bacteria encountered through gardening can contribute to gut microbiome diversity, and homegrown vegetables often contain higher levels of beneficial bacteria than commercially produced alternatives. Children who participate in gardening activities often show increased gut microbiome diversity and better immune function. The combination of physical activity, exposure to soil bacteria, and consumption of fresh vegetables creates multiple pathways for supporting microbial health. The concept of microbial rewilding, deliberately increasing exposure to beneficial environmental bacteria, is gaining attention as a potential strategy for restoring lost microbial diversity. This might involve spending more time in natural environments, reducing the use of antimicrobial products, or even deliberately exposing children to appropriate levels of environmental bacteria during critical developmental periods. However, microbial rewilding must be balanced with appropriate caution about harmful pathogens. The goal is not to eliminate all hygiene practices, but to reduce unnecessary antimicrobial exposures while maintaining protection against genuine health threats. The future of lifestyle medicine will likely include increasingly sophisticated approaches to supporting microbiome health. Personalized nutrition based on individual microbiome analysis may become routine, with dietary recommendations tailored to each person's unique bacterial composition and metabolic capabilities. Probiotic foods and supplements may become more targeted, with specific bacterial strains selected based on individual needs and deficiencies. Environmental interventions, from home design to urban planning, may increasingly consider their effects on human microbial exposures. The integration of microbiome science into public health policy represents another important frontier. Guidelines for antibiotic use, food safety regulations, and environmental standards may need to consider their effects on beneficial bacteria as well as their success in preventing harmful exposures. Educational initiatives to help people understand their microbial partnerships and make informed choices about lifestyle factors that affect gut health will be crucial for translating scientific knowledge into improved public health outcomes. As you settle into rest tonight, consider the countless ways your daily choices have shaped the microbial universe within you. The foods you ate today provided nutrients for specific bacterial communities. The environments you inhabited exposed you to new microbial species. The stress you experienced, the sleep you got last night, the exercise you did or didn't do, all of these factors influence the trillions of organisms that call your body home. These microscopic partners are remarkably resilient and adaptable, responding to your choices with changes in their own growth, metabolism, and community structure. They are your collaborators in health, your partners in the ongoing experiment of being human in the modern world. The wisdom embedded in traditional lifestyles, diverse diets, fermented foods, connection to natural environments, moderate microbial exposures offers guidance for navigating the challenges of modern life, while supporting the ancient partnerships that sustain us. Tomorrow brings new opportunities to nurture these relationships, to make choices that support the thriving of beneficial bacteria while maintaining the conveniences and safety of modern life. Each meal, each environment, each decision about medication or stress management represents a chance to support the invisible ecosystem that supports you in return. The dance between lifestyle and microbiome continues throughout life, shaped by your choices but also shaping your health, your mood, and your well-being in return. Understanding this partnership offers profound opportunities for taking an active role in your own health, working in collaboration with the microbial communities that have been humanity's partners since the very beginning. In the quiet of the night, as your body rests and recovers, your gut bacteria continue their essential work. They process the nutrients from your evening meal, maintain the gut barrier that protects you from harmful substances, communicate with your immune system, and prepare your body for tomorrow's challenges. They are the inheritors of billions of years of evolutionary wisdom, the keepers of metabolic secrets that modern science is only beginning to understand. They are your partners in the magnificent experiment of being alive, shaped by your choices, yet essential to your very existence. The invisible world of the microbiome reveals that health is not just an individual endeavor, but a collaborative effort between human and microbial life. The choices you make about how to live ripple through communities of organisms that span your entire body, influencing not just your own well-being, but the health of the bacterial societies that depend on you for their survival. In understanding these relationships, we discover that caring for our health means caring for entire ecosystems, that wellness extends beyond the boundaries of our human selves to encompass the thriving of all the life forms that make our existence possible. This is the profound lesson of the microbiome. We are never alone, never separate from the vast community of life that sustains and surrounds us. Every breath we take, every meal we eat, every choice we make participates in the ongoing creation of the microbial universe within us. Tonight, as consciousness fades and sleep takes hold, this universe continues its ancient work, maintaining the conditions that make dreams possible, healing the day's small injuries, preparing the ground for tomorrow's growth and renewal. In the darkness, The invisible world inside us glows with the quiet activity of trillions of living partners, each playing their part in the symphony of health that allows us to wake refreshed and ready for another day of collaboration between mind, body, and microbes. The story of our microbial partnerships is ultimately a story of hope that understanding these relationships can help us live healthier, more connected lives. Hope that the wisdom of traditional cultures can guide us through the challenges of modern existence. Hope that the remarkable adaptability of both human and microbial life can help us thrive in an ever-changing world. In embracing our role as ecosystems, we discover not a loss of human uniqueness, but an enhancement of it. We are remarkable not despite our dependence on microbes, but because of it. We are the inheritors of partnerships that have been refined across millions of years, the beneficiaries of collaborative strategies that have made complex life possible. As you drift towards sleep, carry with you the knowledge that you are home to countless forms of life, each contributing to your health and well-being in ways both seen and unseen. You are a universe of cooperation, a walking ecosystem, a living testament to the power of partnership between different forms of life. Rest well, knowing that the invisible world inside you never rests, never stops its essential work of maintaining the delicate balances that keep you healthy and alive. In the quiet collaboration between mind, body, and microbes, the ancient dance of life continues, as it has for countless generations, as it will for generations yet to come. The boundaries between self and other, between human and microbial, between individual and ecosystem, dissolve in the recognition that we have always been more than we appeared to be. We are communities of life, expressions of the creative power that has been shaping and reshaping the living world since the very beginning. In this understanding, we find not just new approaches to health and healing, but new ways of being human in relationship with all the forms of life that make our existence possible. The invisible world inside us becomes visible through science, but its deepest significance lies in what it reveals about the interconnected nature of all existence. Tonight, in the gentle transition from waking to sleeping, from conscious thought to restorative rest, the collaboration between mind, body, and microbes continues its essential work. In this collaboration, we discover who we truly are, not solitary beings navigating an independent existence, but integral parts of the vast, interconnected web of life that spans from the microscopic to the cosmic, from the bacterial to the human, from the invisible to the infinite. Fecal microbiota transplants. In the sterile halls of hospitals around the world, a medical revolution is taking place that would have seemed impossible just decades ago. Doctors are treating life-threatening infections not with antibiotics or surgery, but by transplanting the gut bacteria of healthy donors into sick patients. This therapy, known as fecal microbiota transplantation, represents one of the most dramatic examples of how understanding our microbial partners is transforming medicine. The procedure itself is elegantly simple, though the science behind it is profoundly complex. A healthy donor, carefully screened for infectious diseases and metabolic health, provides a sample of their gut bacteria. This sample is processed in specialized laboratories, where it is filtered, concentrated, and prepared for transplantation. The recipient, typically someone whose gut ecosystem has been devastated by disease or antibiotics, receives these beneficial bacteria through various delivery methods. The story of Margaret illustrates the life-saving potential of this remarkable therapy. At 78 years old, Margaret had developed a severe infection with Clostridioides difficile, a dangerous bacteria that can cause life-threatening inflammation of the colon. The infection had occurred after she received antibiotics for pneumonia, which had eliminated the beneficial bacteria that normally keep C. diff in check. Traditional antibiotic treatments for Margaret's C. diff infection had failed repeatedly. Each time doctors cleared the infection, it returned within weeks, more virulent than before. Margaret was losing weight rapidly, becoming dehydrated, and facing the possibility of surgical removal of her colon or even death from overwhelming infection. As a last resort, Margaret's gastroenterologist, Dr. Elizabeth Chen, recommended fecal microbiota transplantation. The donor was Margaret's healthy adult daughter, whose gut bacteria had been thoroughly tested to ensure they were free of pathogens and rich in beneficial species. The transplantation process was surprisingly straightforward. The prepared bacterial solution was introduced into Margaret's colon during a routine colonoscopy procedure. The healthy bacteria from her daughter immediately began establishing themselves in Margaret's gut, competing with the C. diff bacteria for space and nutrients. The results were nothing short of miraculous. Within 24 hours, Margaret's symptoms began to improve. Within a week, testing showed that the C. diff bacteria had been eliminated from her gut. Follow-up analysis revealed that her gut microbiome had been fundamentally transformed, now resembling that of her healthy daughter rather than the devastated ecosystem that had existed before transplantation. 6 months later, Margaret remained healthy, her gut ecosystem having maintained the beneficial bacterial communities introduced through the transplant. She had gained back the weight she had lost, her energy had returned, and comprehensive testing showed a diverse, stable microbiome that provided protection against future infections. Dr. Alexander Koretz, a gastroenterologist at the University of Minnesota, who pioneered much of the early research on fecal microbiota transplantation, describes the therapy as bacterial ecosystem restoration. His work has shown that FMT can achieve cure rates above 90% for recurrent C. diff infections, far exceeding the success rates of conventional antibiotic treatments. The success of FMT for C. diff infections has led researchers to explore its potential for treating other conditions linked to gut microbiome dysfunction. Clinical trials are underway testing FMT for inflammatory bowel disease, obesity, autism spectrum disorders, depression, and even neurodegenerative diseases like Parkinson's and Alzheimer's. The case of Robert, a 35-year-old teacher with severe ulcerative colitis, demonstrates the expanding applications of microbiota transplantation. After years of failed treatments with conventional medications, Robert was facing the possibility of surgical removal of his colon. His quality of life had deteriorated dramatically, with frequent hospitalizations and an inability to maintain normal activities. Robert enrolled in a clinical trial testing FMT for inflammatory bowel disease. The donor was carefully selected based on gut microbiome analysis, choosing someone whose bacterial composition showed optimal diversity and anti-inflammatory characteristics. The treatment protocol involved multiple transplantations over several months to ensure successful establishment of beneficial bacteria. The results exceeded everyone's expectations. Robert's inflammation markers dropped dramatically within weeks of the first transplant. His symptoms improved steadily, and colonoscopy examinations showed healing of intestinal tissue that had been damaged for years. 2 years later, Robert remains in remission, his gut ecosystem having been fundamentally reset by the transplanted bacteria. However, the expansion of FMT beyond C. diff infections raises complex cultural, ethical, and regulatory questions that society is only beginning to grapple with. The idea of transplanting human waste, even for medical purposes, challenges deep-seated cultural taboos and requires careful consideration of consent, safety, and standardization. Dr. Monica Fisher, a bioethicist at the University of California, San Francisco, has studied the ethical implications of microbiota transplantation. Her research has identified several areas of concern, including the long-term effects of introducing foreign bacterial communities, the potential for transmitting unknown pathogens, and questions about informed consent when the full implications of treatment are still being discovered. The selection of appropriate donors represents another complex challenge. Current screening protocols focus on infectious disease testing and basic metabolic health, but researchers are beginning to understand that donor characteristics like diet, exercise habits, mental health status, and even personality traits may influence the bacterial communities being transferred. Some recipients of FMT have reported unexpected changes in food preferences, mood, or behavior following treatment, raising intriguing questions about how gut bacteria influence personality and identity. While these changes are typically positive and associated with improved health, they highlight the profound interconnections between gut bacteria and human psychology. The cultural barriers to FMT acceptance vary significantly across different societies and communities. In some cultures, the concept of using human waste for medical treatment conflicts with religious or cultural beliefs about cleanliness and bodily integrity. Healthcare providers must navigate these sensitivities while ensuring that patients have access to potentially life-saving treatments. Efforts to overcome these barriers have led to the development of more palatable delivery methods for FMT. Instead of traditional enemas or colonoscopy administration, researchers have developed oral capsules containing freeze-dried bacteria that patients can swallow like conventional medications. These capsules, sometimes called crapsules in medical humor, make the treatment more acceptable to many patients while maintaining therapeutic effectiveness. The standardization of FMT represents another significant challenge. Unlike conventional medications with precisely defined chemical compositions, microbiota transplants contain living, evolving communities of bacteria that can vary significantly between donors and even between samples from the same donor. Researchers are working to develop standardized bacterial preparations that could provide consistent therapeutic effects while reducing safety risks. These efforts involve identifying the specific bacterial species responsible for therapeutic benefits and creating defined mixtures that could replace whole stool transplants. The regulatory landscape for FMT is still evolving, with different countries taking varying approaches to oversight and approval. In the United States, the FDA has allowed FMT for recurrent C. diff infections under special protocols, while requiring more rigorous clinical testing for other conditions. European regulators have taken similar approaches, balancing the need for safety with recognition of the therapy's life-saving potential. The commercialization of FMT has raised additional ethical questions about access and equity. As companies develop standardized microbiota products, concerns arise about whether these treatments will be affordable and accessible to all patients who could benefit from them, or whether they will become expensive therapies available only to those with adequate insurance or financial resources. International collaboration in FMT research is essential given the global nature of gut microbiome science and the need to understand how genetic, dietary, and environmental factors influence treatment outcomes across different populations. Large-scale studies involving diverse patient groups are needed to optimize donor selection, treatment protocols, and patient outcomes. The future of microbiota transplantation may involve increasingly sophisticated approaches, from personalized donor matching based on detailed microbiome analysis to the use of engineered bacterial communities designed for specific therapeutic purposes. As our understanding of gut bacteria function deepens, treatments may become more targeted and predictable. As you settle into rest tonight, consider the remarkable implications of a therapy that treats disease by restoring the bacterial communities that have co-evolved with humans for millennia. FMT represents more than just a new medical treatment. It embodies a fundamental shift toward understanding health as an ecosystem property, rather than simply the absence of disease. The frontier of biotech. In the laboratories of biotechnology companies around the world, scientists are moving beyond simply transplanting natural bacterial communities toward engineering entirely new forms of microbial life. They are creating designer bacteria programmed with specific therapeutic functions, developing sophisticated delivery systems that can target particular areas of the body, and imagining a future where microbial medicine is as precise and predictable as any pharmaceutical intervention. This frontier of synthetic biology represents perhaps the most ambitious application of microbiome science, promising treatments that were pure science fiction just decades ago. Yet it also raises profound questions about the wisdom and safety of fundamentally altering the microbial ecosystems that have sustained human life for millions of years. The story of synthetic biology begins with the recognition that, while natural bacteria are remarkably sophisticated, they are not necessarily optimized for specific therapeutic purposes. Evolution has shaped gut bacteria to survive and reproduce in the competitive environment of the human intestine, not necessarily to produce optimal amounts of particular therapeutic compounds or to respond predictably to medical interventions. Dr. Pamela Silver, a systems biologist at Harvard Medical School, has spent years developing techniques for engineering bacteria with novel therapeutic capabilities. Her laboratory has created bacterial strains that can detect disease markers in the gut and respond by producing specific therapeutic compounds, essentially turning gut bacteria into living diagnostic and treatment systems. One of the most promising applications involves engineering bacteria to produce precisely controlled amounts of neurotransmitters for treating mental health conditions. Unlike conventional antidepressants that affect brain chemistry systemically, these engineered bacteria could produce serotonin, GABA, or other neurochemicals directly in the gut, where they can influence the gut-brain axis without the side effects associated with pharmaceutical interventions. The case of David, a software engineer struggling with treatment-resistant depression, illustrates the potential of this approach. Traditional antidepressants had provided only limited relief and came with side effects that interfered with his work and relationships. When he enrolled in a clinical trial testing engineered probiotic bacteria for depression, he was skeptical but hopeful. The engineered bacteria had been programmed to produce specific amounts of serotonin and other mood-regulating compounds in response to chemical signals in the gut environment. Unlike conventional probiotics that might or might not survive in the gut ecosystem, these bacteria were designed to establish themselves reliably and function predictably. Over 12 weeks, David's depression symptoms improved gradually but significantly. Unlike his experience with pharmaceutical antidepressants, he experienced no sexual side effects, weight gain, or cognitive dulling. Blood tests showed that the engineered bacteria were functioning as designed, producing steady levels of therapeutic compounds that supported his mental health without disrupting other biological systems. The precision possible with engineered probiotics extends far beyond mental health applications. Companies like Synlogic and Vedanta Biosciences are developing bacterial therapies for metabolic disorders, cancer treatment, and autoimmune diseases. These engineered microbes can be programmed to produce specific enzymes, break down particular toxins, or modulate immune responses in highly targeted ways. For rare genetic diseases that prevent the body from producing essential enzymes or metabolizing certain compounds, engineered gut bacteria could serve as living factories, continuously producing the missing biological machinery. This approach could provide treatment for conditions that currently have no effective therapies, while avoiding the need for frequent injections or other invasive treatments. Dr. James Collins, a bioengineer at MIT, has developed bacterial systems that can function as programmable therapeutics, capable of sensing disease conditions and responding with appropriate treatments. His work has shown that bacteria can be engineered to detect inflammation, tumor markers, or metabolic dysfunction, and automatically adjust their therapeutic output accordingly. The development of sophisticated delivery systems represents another frontier in microbiome biotechnology. Traditional probiotics face significant challenges in surviving stomach acid, establishing themselves in competitive gut environments and reaching specific target tissues. New encapsulation technologies and targeted delivery systems are addressing these limitations. Microencapsulation techniques can protect beneficial bacteria during their journey through the digestive system, ensuring they reach the appropriate location in the gut before being released. Some systems use pH-sensitive coatings that dissolve only in specific areas of the intestine, while others respond to particular chemical signals to release their bacterial cargo at optimal times and locations. Targeted delivery systems are being developed that can direct therapeutic bacteria to specific organs or tissues beyond the gut. Researchers are exploring ways to use engineered bacteria to treat liver diseases, brain disorders, and even cancer by programming them to migrate to particular body sites and produce therapeutic compounds locally. The case of Lisa, a woman with a rare liver enzyme deficiency, demonstrates the potential of targeted bacterial therapy. Her genetic condition prevented her liver from processing certain amino acids, leading to toxic buildup and progressive organ damage. Traditional treatments required frequent hospital visits for specialized medications with limited effectiveness. Lisa enrolled in a trial testing engineered bacteria designed to produce the missing liver enzyme and migrate from the gut to liver tissue. The bacteria were programmed with sophisticated targeting systems that allowed them to cross the gut barrier, travel through the bloodstream, and establish therapeutic colonies in the liver. Over 6 months, Lisa's liver function improved dramatically. The toxic amino acid levels in her blood decreased, her liver inflammation subsided, and her overall health stabilized. The engineered bacteria had essentially provided her with a missing biological function, allowing her liver to process compounds that her genetic condition had prevented. However, the development of engineered probiotics and synthetic biology applications raises significant regulatory and safety concerns that the biotechnology industry and government agencies are still learning to address. Unlike conventional medications with well-defined chemical compositions and predictable effects, engineered bacteria are living systems that can evolve, multiply, and potentially interact with natural microbial communities in unexpected ways. Dr. Drew Dye, a bioengineer at Stanford University and a leading voice in synthetic biology ethics, emphasizes the need for careful consideration of the long-term implications of releasing engineered organisms into human bodies and potentially into the environment. His work focuses on developing safety systems and containment mechanisms that can prevent engineered bacteria from causing unintended consequences. Containment strategies for engineered probiotics include programming bacteria with genetic kill switches that cause them to self-destruct after completing their therapeutic functions, or with dependencies on artificial nutrients that are not available in natural environments. These approaches aim to prevent engineered bacteria from persisting indefinitely or spreading beyond their intended therapeutic targets. The regulatory approval process for engineered probiotics is more complex than for conventional drugs, requiring evaluation of both the therapeutic effects and the potential ecological impacts of introducing novel organisms into human microbiomes. Regulatory agencies are developing new frameworks for assessing the safety and efficacy of living therapeutics, while ensuring that innovation can proceed responsibly. International coordination in synthetic biology regulation is essential given the global nature of both human health and microbial ecosystems. Different countries are taking varying approaches to oversight, creating challenges for companies seeking to develop and market engineered probiotics internationally. The intellectual property landscape for synthetic biology is also evolving, with questions about whether living organisms can be patented and how to protect innovations while ensuring broad access to life-saving therapies. These issues become particularly complex when engineered bacteria are designed to replicate functions that exist naturally in some people, but not others. Public acceptance of synthetic biology applications in medicine faces cultural, religious, and philosophical barriers similar to those encountered with other biotechnologies. Some people express concern about playing God by creating novel forms of life, while others worry about the long-term consequences of introducing artificial organisms into natural ecosystems. Educational initiatives aimed at helping the public understand both the potential benefits and risks of synthetic biology are crucial for informed decision-making about these technologies. These efforts must address legitimate safety concerns while avoiding both naive technophilia and reflexive technophobia. The convergence of artificial intelligence with synthetic biology is creating new possibilities for designing and optimizing engineered probiotics. Machine learning algorithms can analyze vast amounts of data about bacterial function, host interactions, and therapeutic outcomes to design more effective and safer microbial therapeutics. AI-driven approaches can help predict how engineered bacteria will behave in complex biological environments, optimize their therapeutic functions, and minimize potential side effects. These tools may accelerate the development process while improving the safety and efficacy of synthetic biology applications. The environmental implications of synthetic biology extend beyond individual human health to include potential effects on broader microbial ecosystems. Engineered bacteria released into human bodies could potentially interact with environmental microbes through sewage systems or other pathways, requiring careful monitoring and assessment of ecological impacts. Some researchers advocate for the development of biocontainment systems that would prevent engineered bacteria from surviving outside their intended therapeutic environments. Others argue for gradual, carefully monitored introduction of synthetic biology applications with robust tracking and recall mechanisms. The future of synthetic biology in medicine may include increasingly sophisticated applications, from bacteria that can perform complex diagnostic functions to microbial systems that can adapt their therapeutic output based on real-time monitoring of patient health status. The integration of synthetic biology with other emerging technologies like nanotechnology and biotechnology could create powerful new therapeutic possibilities. As you contemplate these remarkable possibilities from the comfort of your rest, consider that we stand at a unique moment in human history. For the first time, we possess not just the knowledge to understand our microbial partners, but the power to redesign them according to our therapeutic needs and desires. This capability brings enormous potential for treating diseases and enhancing human health, but it also requires wisdom, caution, and careful consideration of the long-term implications for both individual and planetary health. The future of the human self. In the quiet moments before sleep, as your consciousness settles into rest, a profound question emerges from the depths of scientific discovery. If trillions of microbes influence your thoughts, shape your emotions, and determine much of your health, who are you really? Are you the human cells that carry your genetic code? Or are you the entire ecosystem of human and microbial life that functions as an integrated whole? This question, once the domain of philosophy and speculation, has become a pressing scientific and practical concern as our understanding of the microbiome reveals the extent to which we are not individual organisms, but superorganisms, complex communities of life that function together as a unified biological entity. The concept of humans as superorganisms represents a fundamental shift in how we understand identity, consciousness, and the very nature of being human. We are not merely inhabited by bacteria. We are communities of life, ecosystems in which human and microbial components collaborate so intimately that the boundaries between self and other become meaningless. Dr. Lynn Margulies, the visionary biologist who first proposed that complex cells evolved through bacterial cooperation, understood decades ago that life at every level involves partnerships between different organisms. Her work laid the foundation for recognizing that humans, like all complex life forms, are not individuals but communities that have learned to function as unified wholes. This understanding has profound implications for medicine, identity, and the future of human health. If we are superorganisms, then optimal health requires not just the wellness of human cells, but the thriving of entire microbial ecosystems. Disease becomes not just a malfunction of human biology, but an imbalance in the complex relationships that constitute our expanded selves. The medical implications of the superorganism perspective are already transforming healthcare in ways that would have seemed impossible just decades ago. Rather than treating humans as isolated biological machines that occasionally break down, medicine is evolving toward understanding health as an ecosystem property that emerges from the harmonious function of countless different life forms working together. Preventive medicine of the future will likely focus as much on maintaining microbial health as on traditional human health indicators. Regular microbiome analysis may become as routine as blood pressure monitoring, providing early warning signs of imbalance before symptoms appear. Interventions to support microbial diversity and function may become standard components of preventive care. The story of Emma illustrates this shift toward ecosystem-based healthcare. As a healthy 32-year-old with no obvious health problems, Emma might never have considered her gut bacteria until she enrolled in a longitudinal microbiome study. Regular analysis of her gut bacteria over 2 years revealed gradual changes that preceded the development of inflammatory markers by months. Working with physicians who understood microbiome science, Emma was able to address these microbial imbalances through dietary changes and targeted probiotics before any symptoms developed. Follow-up testing showed restoration of bacterial diversity and reduction of inflammatory markers, potentially preventing the development of chronic disease. This personalized, predictive approach to healthcare represents the future of medicine in the age of the microbiome. Rather than waiting for disease to manifest in human symptoms, healthcare providers will monitor the health of entire bacterial ecosystems and intervene to maintain balance and prevent dysfunction. Mental health treatment is already being transformed by understanding the gut-brain axis and the role of gut bacteria in psychological well-being. The future may bring sophisticated interventions that combine traditional psychological therapies with microbiome-targeted treatments to address depression, anxiety, and other mental health conditions more effectively than either approach alone. Dr. Ted Dinnan, a psychiatrist at University College Cork, who coined the term psychobiotics, envisions a future where mental health treatment routinely includes analysis of gut bacteria composition and targeted interventions to support beneficial microbes that influence brain function. This approach could provide more effective treatments with fewer side effects than current pharmaceutical interventions. The case of Michael, a teenager struggling with severe depression that had not responded to conventional treatments, illustrates this integrated approach to mental health care. Comprehensive analysis revealed that his gut microbiome lacked several bacterial species known to produce neurotransmitters and anti-inflammatory compounds. Treatment combined traditional cognitive behavioral therapy with targeted interventions to restore his gut microbiome diversity. Over 8 months, as his bacterial ecosystem recovered, his depression symptoms improved significantly. The integration of microbiome science with psychological treatment provided relief that neither approach had achieved alone. Personalized nutrition based on individual microbiome composition represents another frontier in superorganism medicine. Rather than generic dietary recommendations, the future may bring precisely tailored nutrition plans based on each person's unique bacterial ecosystem and metabolic capabilities. Companies are already developing technologies that can analyze gut bacteria composition and provide specific dietary recommendations to support optimal microbial function. These systems consider not just human nutritional needs, but the dietary requirements of beneficial bacteria, creating feeding strategies that support the entire superorganism. The story of Roberto, a professional athlete seeking to optimize his performance, demonstrates this personalized approach to nutrition. Microbiome analysis revealed that his gut bacteria were poorly suited to metabolizing the high-carbohydrate diet typically recommended for endurance athletes. His bacterial composition suggested he would perform better on a diet higher in protein and healthy fats. Adjusting his nutrition to support his unique microbiome composition led to improvements in energy levels, recovery time, and overall performance. The personalized approach based on bacterial analysis provided benefits that generic sports nutrition recommendations had not achieved. The philosophical implications of the superorganism perspective challenge fundamental assumptions about identity, consciousness, and free will. If gut bacteria influence mood, decision-making, and even personality traits, what does this mean for concepts of individual autonomy and personal responsibility? These questions become particularly relevant as research reveals the extent to which gut bacteria can influence behavior, food preferences, and even social interactions. The bacteria in your gut may influence your cravings for certain foods based on their own nutritional needs. They may affect your mood and social behavior through their production of neurotransmitters and other bioactive compounds. Dr. Beatrice de Gelder, a cognitive neuroscientist at Maastricht University, has studied how gut bacteria influence social cognition and emotional processing. Her research suggests that the microbial composition of gut bacteria may influence empathy, social connectivity, and even moral decision-making through effects on brain chemistry and function. This research raises profound questions about the nature of human agency and identity. Are the choices we make truly our own, or are they influenced by the metabolic needs and biochemical outputs of our microbial partners? How do we understand concepts like personality, character, and individual responsibility in light of these intimate biological partnerships. Rather than diminishing human uniqueness or agency, the superorganism perspective may actually enhance our understanding of human complexity and capability. We are remarkable not despite our dependence on microbes, but because of our ability to integrate countless different forms of life into functional, conscious wholes. The collaborative nature of the superorganism suggests that human consciousness and intelligence emerge from the coordinated activity of many different biological systems, including both human and microbial components. This distributed model of consciousness aligns with emerging neuroscience research showing that mental phenomena arise from complex networks rather than single brain regions. The future of human enhancement may increasingly focus on optimizing the entire superorganism rather than just human components. Interventions to improve cognitive function, emotional resilience, or physical performance may target gut bacteria as much as human biology. The enhancement of human capabilities may require the enhancement of microbial partners. Longevity research is already revealing connections between gut microbiome diversity and healthy aging. Centenarians often maintain remarkably diverse gut microbiomes despite their advanced age, suggesting that microbial health may be crucial for extending healthy lifespan. Future interventions to promote longevity may focus heavily on maintaining and restoring microbial diversity throughout life. The environmental implications of the superorganism perspective extend beyond individual health to include our relationship with planetary ecosystems. The bacteria in our bodies connect us to soil microbes, ocean bacteria, and atmospheric microorganisms in complex webs of microbial exchange that span the globe. Understanding humans as superorganisms may lead to greater appreciation for the importance of environmental health for human health. The destruction of natural habitats, the overuse of antibiotics in agriculture, and the pollution of microbial environments ultimately affect the bacteria that live within us and support our health. The conservation of microbial diversity may become as important as the conservation of plant and animal species. Some bacteria that once lived in human guts may already be extinct, lost to antibiotic overuse and environmental degradation. Efforts to preserve microbial diversity in traditional populations may become crucial for maintaining human health in the future. The social implications of superorganism science include recognition that microbial health is not just an individual concern but a community responsibility. Family members share microbes, communities share environmental bacteria, and societies share the consequences of policies that affect microbial ecosystems. Public health initiatives of the future may focus as much on supporting beneficial bacteria as on preventing harmful pathogens. Urban planning may consider microbial exposures in the design of buildings and public spaces. Educational curricula may include understanding of microbial partnerships as fundamental to human biology and health. The global implications of microbiome science include recognition that microbial diversity is unequally distributed around the world, with industrialized populations generally having less diverse gut microbiomes than traditional societies. This microbiome inequality may contribute to health disparities and could inform international development and public health strategies. Efforts to address global health challenges may need to consider microbial factors alongside traditional medical interventions. Programs to improve nutrition, sanitation, and healthcare delivery may need to account for their effects on beneficial bacteria as well as their success in preventing infectious diseases. The technological convergence of microbiome science with artificial intelligence, nanotechnology, and biotechnology may create unprecedented opportunities for monitoring, understanding, and optimizing superorganism health. Real-time monitoring of gut bacteria composition and function may become routine, providing continuous feedback on health status and early warning of potential problems. Wearable devices that can analyze breath, skin, or other easily accessible samples may provide continuous monitoring of microbial health alongside traditional health metrics like heart rate and blood pressure. This real-time feedback could enable immediate interventions to maintain optimal bacterial balance and prevent disease development. The integration of microbiome data with other health information through advanced AI systems may provide insights into optimal health strategies that account for the complex interactions between human and microbial biology. These systems could provide personalized recommendations for diet, exercise, stress management, and medical interventions based on comprehensive understanding of superorganism function. As you drift towards sleep tonight, consider the remarkable transformation in human self-understanding that microbiome science has brought about. The boundaries between self and other, between human and microbial, between individual and ecosystem, have dissolved to reveal a more complex, more interconnected, and ultimately more wonderful truth about what it means to be human. You are not alone in your own body. You never have been. You are home to countless forms of life that have co-evolved with humans for millions of years, partners in the magnificent experiment of consciousness and complexity that we call human existence. The future that emerges from this understanding is one of unprecedented possibilities for health, longevity, and human flourishing, but also one that requires wisdom, humility, and respect for the ancient partnerships that make our existence possible. We are not masters of our biological destiny, but collaborators in ongoing relationships that began long before we existed and will continue long after we are gone. In embracing our nature as superorganisms, we discover not a loss of human uniqueness, but an enhancement of it. We are remarkable because we have learned to integrate countless different forms of life into functional, conscious wholes. We are extraordinary because we participate in partnerships that span the tree of life, connecting us to every other living thing on Earth. The invisible world inside us is invisible no more, revealed by science to be a universe of cooperation, communication, and collaboration that creates the conditions for consciousness, health, and life itself. In understanding this world, we understand ourselves more completely than ever before, not as isolated individuals, but as expressions of the fundamental interconnectedness that characterizes all existence. Tonight, as consciousness fades and sleep takes hold, the superorganism that is you continues its ancient work. Human and microbial components collaborate in processes of repair, renewal, and regeneration that prepare you for tomorrow's possibilities. In the darkness, the invisible becomes visible, the separate becomes connected, and the individual becomes part of something infinitely larger and more wonderful than could ever be achieved alone. Rest well, superorganism. Dream deeply, community of life. Tomorrow awaits, and you will meet it not as a single organism but as an ecosystem, not as an individual but as a universe, not as separate but as essentially, fundamentally, magnificently connected to all the life that has ever been and ever will be. The future of the human self is not human alone, but human in partnership with the microbial world that has shaped our evolution and continues to shape our daily existence. In this partnership, we find not just new possibilities for health and healing, but new ways of understanding what it means to be alive, conscious, and gloriously, wonderfully, impossibly complex. The story of mind, body, and microbes is ultimately the story of life itself, cooperative, interconnected, endlessly creative and more beautiful than we ever dared imagine. In embracing this story, we embrace our true nature as participants in the vast, ongoing experiment in partnership and collaboration that we call existence. In the quiet of the night, the collaboration continues, as it has for billions of years, as it will for eons to come. The invisible world inside us glows with the activity of countless partners in the magnificent dance of being alive, ensuring that when we wake not alone but accompanied by the ancient wisdom of microbial life, ready to continue the eternal partnership between mind, body, and the microscopic universe that makes it all possible.